आईडी से कही हेलो माइक टेस्टिंग हेलो हेलो आ रही है
Connected. All good? Yeah? Should we start? All right. So how's everyone doing? Good? Okay. Does anyone remember what we talked about last week? Yes? Okay. All right. Did anyone do the case study? Some? Yes? No? Maybe? Pick one. Which one have you picked up? If anyone wants to give the example of which one did you pick up? Not yet? Okay. All right. Make sure that you do, because I'm not sure, but how maybe Professor Sahu might want to basically have a look at two of them and have them present here, if anyone has interest in it, right? Okay? All right. I'll have one more case study, which is more related to the hopefully Indian environment. So we'll see that. We'll probably introduce it tomorrow, and then we'll see how exactly it goes with that. Any questions from what we did last week? Yes, no, maybe it's an opportunity to say that I didn't get anything. Start all over again. Maybe we'll do that, but I'm not sure. All right, no questions. Then let's just continue. What we're going to do today is that a little bit that was left from last week, which was more about the attention and the transformer. Two things that you should probably know if you kind of claim that we did something about generative AI or large language models. So got to know something about it. I have shifted focus from last 2 days or so, if you notice about it. All I wanted to do most is that you get the intuition of what's going on inside those systems, not necessarily all the calculus or all the mathematics that go behind it, right? So very quickly, if you remember that, this is what we have been talking about all along. Now, I've put a lot of these diagrams here. You will see them in the next hour or so, one at a time, and then try to figure out what exactly is going on. Basically, two things are clear, that they're not the databases. So it's not that you're asking a question and a system is running through their database and then trying to find the right match or the right answer. They're not. They are a model. That's why we call them as model, right? We're not calling them as systems per se, but they're a model which is trying to put together words in some shape or form, right? So if you look at it, I said something about functions. We talked about surfaces. We talked about the neural networks, and we talked about a latent space, right? These are how words are organized roughly. So we're going to look into all of these things one more time, this time from the perspective of transformer and attention, right? Has anyone heard the term attention before in the context of large language models? No? Okay. All right. So let's try to understand why we need that concept, right? And as again I'm saying that, let's just try to get an intuition of what exactly we're doing. Now, clearly what we have understood after the week one, that every time we're running the model, it's trying to predict the next most probable word that will fit into a sentence. So if, let's say, it has seen the best thing about AI is its ability to. Now, how does it predict the next word? Now, there could be a possibility that the best thing about its ability to learn, predict, make, understand, do, like a lot of common questions are possible, right? So there is no right or wrong answer. So that's number one. That's where we moved from sigmoid to softmax, if you remember that. What we need to do here, or what the system or what the model does, is that it tries to figure out what are the most probable answer, and it assigns them probability. Right? So if you look at this example, and I'm not saying that these are the only words it will pick up or these are the only kind of probabilities it will get, which word is more likely to be picked by the model? Come on, have a look at it. We have the choices and we have the probabilities. Learn. Anyone who disagrees or wants to say something different? Yes, if we are picking up the highest probability one, then obviously it will pick learn, but we know that we can actually tweak it by having those parameters top P, top K, because if it is always picking the highest probability, there's not going to be any variation. You will always get the same response. Right? This is what we talked about last week. So, and then it keeps on doing this in the sense that every time it picks a word, then it looks at the whatever the sentence it has so far and then says what's going to be the next word. So let's say it did not pick the learn, let's say it picked the create, which is not even here. So you say create words that are both exciting and so forth, continues, right? That's a very simple way the generative AI is functioning and or predicting every new word that it is coming along. That's clear, right? No confusion on that. So let's just continue to see if we are changing, then you can see that if it picks learn, it might go in a different route. If it picks the ability to really, it can go in a different sentence altogether, examine. That's where you see that, because we do not want it to be predictive all the time, in the sense that you know that if I give it this prompt, this answer will come. And that's where it has, in a way, if you think about a little bit of a conflict also. Because if you're giving it a prompt, the Kumbh is in 2025 is happening at Prayagraj. You don't want the randomness to say that one time it says Prayagraj, next time it says Ujjain, then Haridwar. So in some cases you do want it to give predictable, correct answers. In some cases you want it to be a little bit random. That randomness is two sources. One obviously is your tuning parameters, because you're telling it how random you want the answer or how definitive you want the answer. And the second thing is this, for it to understand how best it understands the meaning of the words, right? The meaning of the words are important, and that's where the attention will come in. Okay? So if you look about it, this is a kind of graph that's coming in terms of what exactly are the possible words it's looking at, and then trying to figure out which one to pick. Now, where do these probabilities come from? You saw these probabilities here, right? 4.5%, 3.5%. Does someone remember where these probabilities are coming from? We looked at the bare minimum or a simple example. But where do these probabilities come from? Any idea? Come on. Sorry? Yes, but what's the input to that function? Alright, so what did we say? We said that all these models learn, that learning leads to weights and biases. Those weights and biases are fed into a function. In this case, it will be softmax. So then what happens is that based on the weights and biases, and we looked into it, that these weights and biases follow a special equation, and then they are being summed up, and those summed up values are sent to the softmax, and then if there are 10 different potential choices, the probabilities are calculated, yes, based on the base probability, right? That's where these probabilities are coming from. Just keep that in mind, where these probabilities are coming from. So when you have started with the very first word, the, right? A lot of options exist. That those probabilities start from very beginning based on like what you have seen. So it will go back in its history and say, if I see the first word as the, what would be the next possible word? And keep in mind, it may choose the totally wrong word. It may choose a word that you did not intend it to be chosen. How do you kind of tell the model to choose what you wanted to choose? Prompt engineering. That's what you're telling the model, because the model doesn't know what you intend it to do. Your intent is conveyed to the model using the prompt that you are providing. Now, all of you have access to, let's say, same model, right? ChatGPT. How well your prompt is will determine how well the model responds to your prompt. Right? All right. So that's what you show your intent to the model, but the model still has to have some probabilities to begin with. Those probabilities are coming from the learning. Now, think about it. We said that they are learning a word at a time. But what if the model is learning one letter at a time? So not the word the, but really the first letter T, then H, then E. Is that going to be better, or is that going to be not so good? What do you think?
Not so good.
Why? Why? I mean, I agree. The answer is correct, but then why? We should always ask.
More complex
More complex?
for the model to predict.
Okay. So, yes, to some extent. So, what we're going to say that here, not all combinations of the letters are the correct acceptable words in English, right? So, THE is a word that has a meaning, but TEH is not. In a way, there's no semantics attached to that. So, yes, you can start with one letter at a time, but it increases the size of the learning space. And then majority of that space will consist of letters or words or combination of letters which are not having any meaning or meaningful semantics attached to that. Having said that, we're going to use the example here again for intuition, how the model is learning. Okay, so on the or your left hand side, you see the distribution of each individual alphabet in the English language text, which, let's say, some model has seen as part of its learning. Does that make sense? Which specific alphabet has the highest occurrence in a typical English language text?
E.
That's based on your understanding, or you're looking at the graph?
Looking at the graph.
All right. What's the second one? Right? Okay. So, intuitively, do you think that kind of sounds right? Or somebody might want to disagree with it. So, the J, the Q, and Z are the ones which you don't find very common. E is common, A is common, R, S, T are pretty common, M and N are pretty common, G, H are common. So if you look at the language, the words that you use, you would see that that's the distribution, right? So my point here is that if you're trying to predict the next word in the same probability, IID, if you remember, the same distribution function, that's the distribution function if you're using one alphabet or trying to pick the next alphabet, right? That's what it is. How many of you have played Hangman? Hangman is a game, right? How do you predict the next character or word? You pick a character at a time, right? How do you pick it? Come on, there were only one or two hands going up. Do you know Hangman is a game? No? Oh. All right, so let's play the Hangman now. So Hangman is like you are given a word, you predict an alphabet at a time and try to predict the word.
We know this game.
Huh?
We know this game, but doesn't know.
The name of the game, basically?
Yes.
All right, fine. So who can predict this word? Now, again, there are multiple words like this, but you predict first alphabet and I'll tell you what it is and then we go on that.
A.
Sorry? A. The A goes here. So one wrong.
Is it a question of permutation and combination?
It is, but the game is a game. Let's just try to predict.
E. P.
One at a time. Which one? Who said P?
E. P.
P. Okay. All right. What was it? E. Okay. Now I'm going to ask, I'll stop it here and then I'm going to ask the question, why did you pick A? Who picked A? T? T comes here. Okay. But why did you pick A first? Who's going to give the answer? Like, yeah.
The word is going to have vowels mandatorily, so I started
With the vowel A, E. Yeah, but see, you have the distribution right there. So you should have gone with E first.
and that's why I said E also.
Okay, right. All right. Why P? Who picked P? Okay. All right. And then the whole idea is that if you are picking one character at a time, you should pick going by this distribution because that's the most likely distribution. Having said that, once you have figured out one or two, now you are not picking the individual base probability commands because now you already know it's EEP. Now what it could be? Which one? No, you are picking one alphabet at a time. Okay, one. Okay, which one should I take? S. Okay, let me write the H here first. S here. Okay, T is already gone out here. Yes. Okay, that was the word I have. Okay, the point I'm trying to make here, if you think about it, when you are picking the first one, you should go by that distribution because that's the most common distribution. The moment you've got one character, one position right, it's no longer that one. It's that plus something else. That's the base probability. Given I have already fifth character as P, what would be the fourth one or third one or second one or the first one? Right? If you look at this one, can anyone guess what this is showing? Correct. Now, darker is the color, more likelihood that that combination is going to appear. So if you look at this, this says that a combination of Z and W coming together is a very low likelihood. On the other hand, if you see this, A and M, A and N, A and P, AR, AS, AT have a very high likelihood of occurring together. Is that point clear? Now I can't show you three dimensions, it's just become more and more difficult. But if you think about it, if you start from looking at the probabilities of a single alphabet, two of them together, three of them together, four of them together, you're looking at a probability distribution function, something that we talked about a lot last week, right? Where do these things come from? Learning. As you are sending learning input to the model, it is figuring out that, okay, I saw 13E in 100 characters that I've seen, or 300 in the 3000 that I've seen, or 5 million in 10 billion that I've seen, whatever the number. It's calculating the probability every time. One tuple, two tuple, n tuple, things like that. So keep in mind, all that is going on here is trying to figure out the probabilities. That's all it's going on. If you learn that, you will be very, very successful on this game as well, right? Try to figure out. Now, why we are not doing one word at a time? A, because that probability is not sufficient, because we are trying to kind of depict higher level constructs. Second thing is that, as I mentioned earlier, not every two alphabet combinations are the valid words. Can it still produce meaningful sentences? Yes, it can, but it's going to take longer. So here is an example. It's trying to predict random words with increasingly going by 2 grams, n gram. Now, n gram basically means that the combination that you're doing. 2 grams means the two words together. So this is an experiment that started with random words being created with 2 alphabets or 3 alphabets at a time. Makes no sense. You keep going on multiple iterations, then in the 5th iteration it started forming words which had some meaning in English. So the point here is that if you're trying to generate sentences, it may not be worthwhile starting from a single character as a unit. It's better to go with a larger character. Now look at the other side. If you tell the model that treat every word like a 5-character word, is that a good thing? Right? Even that is not a good thing, because if you say 5, this has every word which is more than 5, right? But it missed out on was. It missed out on high. I mean, I'm just not saying that it did, but it won't, because if you tell it that every word will be 5-character, it will miss out ale, for example. It will say that that's not complete, that's incomplete. So what people realized, or researchers realized, that we don't want 1 character as a starting point. We don't want to give it like a 5-character that you have to form a 5-character. Let the model figure out what's the best size, or which is the best word to keep it. Say, for example, it might decide that, where did the high go? Yeah, high is occurring enough number of times so that it deserves to be counted as something important. OIA probably is not occurring as many times as whatever warrants special attention, so it need not be what we are interested in. So really what is going on here in modern models is that we are not telling them either pick 1 character at a time or pick at least 5. Let them discover based on their own learning that what's the most appropriate size of, now let me introduce a new word, token. So we're not calling it a character, we're not calling it a word, we call it as token. The size of the token is not predetermined, it is discovered by the model as it's learning whatever is the underlying text is. Make sense so far? All right. So what is a model? That's what the model is. It estimates probability by which a certain token or sequence of characters will occur in its training data. Yeah? Now, because we are not telling it to use a token size of 1 or 5, what was discovered, this was not intuitive, that it is actually creating the token which were never part of the input data. That's part of its learning. So for example, for whatever it's worth, and I'm not saying that's the one, it may be picking this as a token of interest. I'm just giving an example. So when people started looking at the model or the internals of the model, saying that which token it found interesting, they noticed that, and which is what we were saying here, not this one, too far, yeah, that some of those tokens were not something which were explicitly part of the input data which was used for training, which means the model is trying to say that, or figuring out that, not just the words that you're providing me, I find some more combination or some more sequences of alphabets which are of interest, and I'm using those as tokens as well. Does that make sense? Yeah? All of these are models. We have seen a couple of these examples. That is the original observation on the top, your left corner here. There are multiple functions that are trying to approximate the occurrence of these observations, which is really a model. Now, you have 3 different functions trying to approximate the observed phenomena, and each of these lead to a model. Right? So, let me ask another question. Same question we have asked a couple of times. I asked this morning also. What is the model trying to learn? I mean, one way we mentioned, and then we talked about weights and biases, but let's try to give a slightly higher level definition. The model is trying to learn which function should I use to predict the next token. So, at least for today's lecture, let's use the word token, because we will use that in the context of the LLMs. So, a learning for the model is basically trying to find the right function that approximate the distribution that has been observed. All the words you should know very clearly: observation, distribution, function, all know that, right? Okay. So, couple of things that we did earlier before we get to the transformer and the attention. We saw the example of a single perceptron or a neuron, how that functions. We also determined that single neuron can only approximate a linear function, i.e. it can only do AND and OR but not the exclusive OR. But if we introduce a hidden layer or the layer in the middle of input and output, then we can have it learn the nonlinear functions as well. So one of the experiment that was done was to say that what would it take for a neural network to discover this function? Anybody here who's electrical, electronics or telecommunications? Do you recognize this function? Okay. Sorry? Sorry, say it again. Yes, digital signal, but what would you call that function? Sorry? It's a step function. It's some kind of a step function, right? Now, the idea was that we don't know the amplitude frequency. We can make a determination of it, but it's a step function. Let's say that. Can a neural network learn that function? What do you guys think? I mean, obviously, the answer is yes, because we have come this far. But as the research was starting, we wanted a single input and a single output, and we wanted to see that can we create a neural network that can learn this function. Not that you tell it, you can tell it because we know this is a fairly standard function. Anybody who's doing the, I guess, first year electronics will come across this kind of a function anywhere. The issue was that can we make a neural network that will learn this function by just giving it inputs, not telling it. So, can anyone guess what would have happened or what would be required to do that? So, this is the kind of experiment. So, if you go by this, so this was the structure that we started with. It was very clear that it would not be one neuron that can do it. Researchers started with two different layers here, two hidden layers basically, and single output. So one thing is clear: single input this way, single output, which means that it's a sigmoid function at the end. 4 neurons in the first hidden layer and 3 in the next hidden layer. Now one may argue or ask the question, why 4 and 3? Why not 2 and 3, or why not 5 and 3? That's something which, as I already mentioned, that's kind of research. So here's what was observed. The same structure of the neural network after 10,000 examples. This is the function that was learned. After 100,000 examples, this was the function that it learned. After about 1 million examples, this is the function, and about 10 million examples, it got the function right. Same neural network is just changing the weights and biases to get to the point where it learns the function that we want it to learn. What does it tell you? I mean, is it good? Is it not so good? Or what do you think is going on? So one thing is clear. That's how the research is done. Painstaking. One step at a time. One neuron at a time. You got to repeat it 10 million times. I mean, okay, you don't do it manually. You are writing programs to do it. And those things become the building blocks, right? In the sense that you realize that. So if we go from that example, this is what it was learned, in the sense that single sigmoid, that's the function it learns. That's the linear function. That's the only thing that a single sigmoid can do. You introduce 2 lanes in the hidden, it learns this kind of a function. You have 3 in one hidden layer, it learns this kind of a function. So all of it was learned by the researchers one step at a time. You have this kind of neural network, you do this. To learn this, you need this structure. So you think of it, these are as building blocks. So this was the first section I wanted to cover, in the sense here what the learning is, and then we talked about last week a single neuron And then basically, only thing we said that you need a hidden layer if you want to do a nonlinear function. Now you see that how these things were building one neuron, one layer at a time. And then you start learning more and more complex functions. That's what basically it is, right? Okay. Any questions in terms of figuring out, understanding what we did? The two concepts, if you think that we learned right now, one is the new thing I introduced called token, which we talk about a lot more. And then the second thing is the intuition of n-gram, in the sense that what's the probability distribution if it is 1 character, 2, 3, up to n. And then I said that we are not telling model what should be the size of the token or the words. We said it will learn on its own. And then we saw some examples of how the neural networks learn more and more complex functions. Any questions? Yes, no, maybe? If you have access to any programming network, if you want to make sure that how the neural networks function, just try doing these kind of experiments and then see how exactly. Theoretically speaking, if any of your electronics lab can be simulated using a neural network. Pass on the inputs and outputs, and then you let the models learn. Any questions? Okay, if not, let's move on to the next topic. How do we take these tokens and see that they are used in LLM? So let me, or the neural network. So let me introduce another word called embeddings. I used it last week, last day, in terms of defining what these embeddings are, right? So, what have we understood so far? That when the learning data is provided to a model, it converts the incoming data into tokens. These tokens are not necessarily words and have no fixed size either. What was observed, and I mentioned this on the earlier slide, that it was forming the tokens with the combination of words or combination of the alphabets which were not even necessarily in the input data. Okay. Now, all these tokens, and if you remember that very first diagrams I showed, is a kind of a word cloud, will end up into some kind of a space. We talked about the space, saying that it's a higher dimensional space than we can characterize. But in general, if you think about it, what an embedding is that it is trying to capture or trying to absorb the essence or the meaning of the underlying domain represented by numbers. So this is another key insight that you get here. Even though these large language models or generative AI is dealing with the words, text, and images, or whatever the case may be. We have seen the 3 examples I gave you in the case study. One was audio, one was images, the one was protein data, and those kind of things like health related. Under the cover or behind the scene, it does not understand. It doesn't know what protein is. It doesn't know, or at least that's what we think. But it is converting whatever the meaning is in a combination of numbers. And numbers not necessarily in 2 dimensions, but in a very high dimension numbers. And what researchers are finding, that even though the model doesn't understand what do we mean by mango or papaya or banana, but when you look into its space, these tokens, because for it they are token, all the fruits are together. No one is telling it that mango is a fruit, apple is a fruit, banana is a fruit, and they are related. All it's seeing is these alphabets. It's converting them into string of numbers in some very high dimension. So the concept of embedding is taking a word or a token and assigning it as a sequence of number in a very high dimensional space, so that related concept come together. Nearby things are represented by nearby numbers. Now, this is the beauty of this model that people discover. no one is telling it that alligator and crocodile are related. It doesn't even know that the alligator is some kind of a reptile animal. Still, it's able to figure out that alligator and crocodile are together, and the chimpanzee belongs here, not here. The elephant is in a different kind of a domain. So it's figuring out. All of it is happening by figuring out the right embedding, which is assigning some set of numbers to each token which it finds of interest. Now, this is an example. If you look at the real embeddings, you may not see, okay, I shouldn't say you may not see, you will see these words, but you may see some other tokens also which the model thought they were of interest. Okay? Now, some people started thinking it's sentient because it's learning which no one told it. No one told it. No one told it that papaya and banana and melon are related, but it discovered them. It found it out. Okay? Embeddings. What we do, one other thing, if someone remembers from last week, I mentioned that if you want to go beyond the prompt engineering, the next kind of activity that you can do is retrieval augmented generation, RAG. When you are interacting at the RAG as a application in a RAG, what you're doing is that you're short circuiting the learning process and then embedding the words at this space, at this level. So basically you're trying to influence model by going one level deeper. Okay? So now let's focus a little bit more on the concept of embeddings, or what we call embeddings. Okay? So how do these things look like? Very difficult to visualize because it's a very high dimensional space that we are talking about. Some examples here. Embedding vectors look like this. The cat looks like that one, dog, chair. So for a human, for our understanding, because we can't visualize vectors in higher dimensions, it's very difficult for us to make any sense of what is going on in there. That might be how our brain perceives a cat or a chair as well, right? We don't know that. But that's how we know that, because this is nothing but a computer program and it's holding some data inside, so we can figure out that this is how it looks like. This is how a chair looks like in one version of a large language model based on whatever learning it did. Make sense so far? Okay. Now let me say one more thing which might be quite unintuitive. So this is meaningful, right? Because we can make sense that there would be an embedding or a token for apricot, peach, cherry, pineapple, fig, whatever the case may be. But don't just go by that. For the LLM, every one of these things is also an embedding. This could be temporary, but at the end of the day, if it's predicting the next character, next word for each of these sentences, they are also assigned a vector or assigned the values or numbers that will make them as another embedding. Is that point clear? So if it's predicting or trying to predict where do the probabilities come from, it will learn that where is a token, then it will learn that where do is a token or an embedding, because that's where it tries to find out what is the closest to this in whatever space it has. So these embeddings will continue to grow and will have every intermediate sentence as part of these embeddings as well. That's what my point here was. Okay, so what goes on is that any sequence of token that is, let's say, seen so far will become an embedding, or it will try to find, do I have this already as an embedding in my space? Okay, so think of it now, what I'm saying here. I started half an hour ago, 40 minutes ago, by saying that it is not a facts database. It is not. But everything else is an embedding. So it may not be doing the exact search. Somebody asked last week a question about fuzzy search. In a way, it's saying that, do I have this as an embedding in my space? If not, what's the nearby word, term, token that I have? So there is always a search involved. So literally what's going on is that whatever the tokens you've seen corresponding to the text which is coming input in your prompt, say for example, try to find an embedding that represents those. If it already has it, great. If it's not, let's try to find, either create a new one or try to find the most semantically meaningful next to it. That's all it is doing it. Does that make sense? Okay. If you're using a chat GPT, there is a context size or a window that says 8K. Anyone remember that? Right? GPT-2 had a much smaller window, 3 had a larger window. What's the significance of that? Any idea? Yeah? Anyone? So two things actually. That's the context window. So one thing it's saying is that you can give it a token or a set of tokens which can go this far, and it will consider them to predict the next one. The other way, it says that theoretically it can have a space which has 8,000 dimensions. We haven't seen in the current LLMs that it goes this far. There are examples of up to 2,000 dimensions that it is constructing its embedding. Now what it means that it's not going up to 8,000, it is finding an embedding within the 2,000 dimensions that it either matches with or creates a new one. All right? Fair enough. So that's what it does, and then try to figure out into a new embedding, generates an array from about 50,000 values, which is what every time it thinks that it's producing it. Okay, all right. The same pipeline being implemented multiple times. Nothing is explicitly engineered. Everything is learned from the training data, right? We are all very clear. Let's look at an example or another example of the embedding space here. So, not only the model figures out the positioning of these concepts, it also notices that some things move together. Plaintiff, defendant, trial. Not only it finds that the plaintiff and defendant are close to each other, they are also linked to a trial in some way, shape or form. Now these are all observations that once the model has its embedding, then the researchers are trying to figure out is that how is it doing what it is doing and how is it doing so good. Similarly, it's trying to find out is that, say for example, street and road are very clear. State and property are close to each other. Growth and economy are, science and degree is added together. So a lot of things that it is learning is trying to figure out where exactly they belong, and are there any what is called as semantic laws of motion, which is what it's saying is that if you change a plaintiff, maybe the defendant and the trial will also change. So these tokens, these concepts move together. Okay, this is also a learning that is happening. That semantic law of motion also tells in the sense that how do you create an adjective for a noun or an adverb or a pronoun. So it's also learning that you have on the one side the one tense, on the other side is interpreted, agreed, recognized, authorized, and they're all appearing together. On this side, if you see the adverbs all appearing together, you come this side, the nouns appearing together. So not only it's learning the embedding, but it's also learning the grammar without anyone telling it and organizing it correctly. So that's also something what this model is doing. Example that we had seen last week, but now in the view what I'm defining as meaning space and semantic laws of motions. it's also figuring out is that the relationship between I and C is what ear and here is. Green to go and red to stop. It's also learning that. We saw the example of this one. Men, women is king and queen. It's also figuring out there's a circle between plant, bird, egg, seed. They are relative to each other. All of these kind of things it's learning on its own, and what we are it's emerging a field called meaning space and semantic laws of motion, where the embedded token in a meaning space or a vector space are moving together. Make sense? How many of you are frightened now? The machines are someday becoming so important that they will take over the world. It's learning a lot of things. It's learning a lot of things very fast. Right? Any of you have heard this? I'm writing it, don't ask me to. It's one of the exam, USMLE. I think it's called US Medical. I'm forgetting L, but E's exam. Okay. I'm not sure. What's the entrance exam for medical here? In my days, it used to call PMT or CPMT. NEET. Okay. So USMLE is an exam basically that someone has to, it's kind of an entrance exam to get into an MBBS equivalent degree. Okay. Most of these models actually can write USMLE exam and pass it. So they have gone to that extent that they can write an exam and get enough ranking to get an admission. So it can do the USMLE exam today. All right. So pretty soon you will be fighting against an agent which is coming as a LLM. Probably doing a lot better than you as an individual can do. Okay. So from tomorrow onwards, when we go into the issues related to the risks and ethics of the issues and things like that, keep those things in mind. That think in terms of, because if we change the hat, if we get into the a slightly different angle into this, what you need to think about it is not what the model can do today, but how fast it is learning. So what it would be able to do tomorrow or day after, right? So that's another way of looking at it. All right, any questions? Especially if you're afraid of your future, of your sons and daughters' future in future, but the models are becoming intelligent very fast, no doubt about it. Come on, any questions? No? Yes?
Weddings can be understood as a group of tokens, combination of tokens.
Okay. So we don't use the word combination or group there. So in a way, if you think about it, so I'm going to use the same words that I've used so far. We started with the single alphabet, right? Then we said the n-grams, which are nothing but the groupings of these things. We call it as sequence, right? And then we said that you end up with the words, which basically have some semantic meanings. So then I said two things here. These words are part of the embeddings, but then we realize that not only these are part of the word, part of the embedding, but these intermediate formations in a longer stream of words which make a sentence are also part of these embeddings. And the second thing I said that sometimes you see that things like these are also part of the embeddings. So nowadays the words that's being used is that tokens. That token could be a single word, or it could be a sentence, or it could be a fragment of a sentence. So the words that the two terms that we use is any token is something which is of interest, and a token, when it assigns a probability, becomes an embedding. Right? So what happens, like for example, let's say, and let me bring the RAG here. If you are, let's say, trying to build a system where you say that I am doing it for money laundering. How many of you know money laundering? I mean, the financial management guys. Can you define what money laundering is? Come on, the management guys. Sorry?
Like to show reflect black money as a white in a legal way.
That's you're answering the question why someone will launder the money. But what is money laundering?
Avoid from taxes.
Okay, that's why, but not still what is it? So money laundering is basically when you are either trying to hide or obfuscate the source of the funding. That's the main thing. So what happens is that when you have a transaction, there's a money coming in, there's money going out, right? The source of the money is important because depending on the source, you may have been already taxed or you want to be taxed here. So money laundering is trying to hide the source of money. That's just the definition, right? Have you heard this term called KYC? What does KYC mean? What does that mean? What does know your customer mean? Come on, if anybody's going in a banking job, finance guys, what is KYC? Know your customer means basically what that customer's source of incomes are normally. That's what KYC. So you might say that I do a business, or this customer does a business, this customer has a job, or whatever the case may be. How is that helping? Because the source of incomes are known. A lot of time when you do a transaction, you might see, I mean, I'm not sure here, but you have a lot of money suddenly coming in from this, which is not in line with your normal transaction. The bank will ask, what's the source of this money? Then you might say that, oh, I sold my ancestral land, that's where this money came from. That's all part of KYC. So, I'll tell you why I'm going into that direction. Money laundering is that when you're trying to hide or obfuscate the source of money, the way you do it, there is a term called layering. Have you heard of it? Right? What is layering? So when you cannot hide the source of the money, you try to obfuscate. And you do it by doing layering of transaction. So your aim is to transfer, let's say, $10,000 from here to here. You want to obfuscate, so you're not going to do this. You're going to say 2,000 here, 3,000 here, 1,000 here, 4,000 here. Then they all give it to someone else. They give it to someone else, and then eventually this person gets like 5 transactions of 2,000 each. What you're trying to do, you're trying to create, rather than one transaction, probably like 200 transactions of different amounts, different people, eventually getting it there. That's what we call layering, right? All right. Why I'm saying this, let's say you want to build a model whose job is to detect the money laundering transactions. Now, our language models don't know it, base models don't know it, or foundation models don't know anything about it. That's where this stuff comes in, and you say that I am embedding some tokens where layering has a different meaning. Hide, obfuscate has a different meaning. Source has a different meaning. So you're trying to teach the model specifics about your domain, which in this case is catching the money launderers. So KYC has a meaning. Layering has a meaning, and then we go into more detail about these transactions, or which transactions are relevant, which transactions should it pay attention to. We'll talk about attention in a bit. So that's what is the retrieval augmented generation is. What we are trying to do, we are trying to inject some tokens in the model's semantic space or new embeddings with different probabilities, and then so that it picks those things much more frequent compared to what it would normally do. Make sense? All right. Any other question? Yes, no, maybe? No? All right. So we're going to go into the transformers and attention. As I said that, not too much mathematics, but get the intuition behind it. So even if you do not have a mathematics background, or even if you had a mathematics background, now you want to go into the management, understand how these things are functioning, because these are the most, I'll say, powerful architecture that has been used to build these large language models. All of them are using the deep neural network technology or deep neural network methodology, whichever way you want to call it, right? So far you guys are with me, right? From alphabet to words to tokens to embeddings, and each embedding having a probability, right? Let me bring one more thing that I used earlier, which was the context-free grammar or context-free language. We talked about it a little bit last week. Does anyone remember what the context-free language or context-free grammar was? Come on. Anyone? No? All right. The context-free grammar was that when a sentence meaning can be determined without any confusion, because the grammar does not have any dependence on the context. So if you write a Python program, right, or for that matter Java program, the language will not let you write something which is ambiguous. Not so in English. In English, the semantics of a word is determined by its context, right? Yeah, and that context could be grammar, could be anything related to that. Right? And the same thing is true with Hindi. Everybody understands Hindi, right? So if I write this, let me just give an example here. What does it mean? Right. So, I mean, I gave an example of English last week, but let me say I will try in Hindi. This could mean very different if you put a comma here or a comma here, right? So, even Hindi is not context-free. All of our languages are context-sensitive languages, which means the meaning of a word or a sentence will depend on the context in which it's being used, right? So let's see here. John picks up a magazine. We all understand. What does it mean? That there's a magazine somewhere and he picks it up. Susan works for a magazine. What does that mean? Let's replace the magazine, let's replace the John and Susan with some other names, right? I don't know, Mahesh picks up India Today, right? Now everybody knows that he's not picking up the building of India Today, he's picking up India Today latest version or whatever that is. Whatever, Shama works for India Today. Everybody knows that. Shama is not working for that paper, but that company India Today. So how you interpret magazine depends on the context, right? Bank. Bank is a bank where you deposit money. Bank is also a side of a river. That's also called bank. Banks of the river, banks of the Ganges River, right? Now, where the bank is a financial institution or where it's a land next to a river, how would a model figure out? That depends on context. And it's very simple. You and I can learn, or you and I have learned it over a period of time, and then what the context is. If we are talking about deposits, withdrawal, check, money, then probably the bank is a financial institution bank. If we are talking about the Kumbh, Ganges, rivers, the Mela, whatever the case may be, then the bank is probably the side, the land around the river or land around the water body. How would you make a model learns that the word's meaning depends on the context? Because if you want your model to be smart, they need to understand that words often have different meanings or different meanings based on the context. And clearly, we are not teaching the models these things, that the banks have two meaning, and in this setup, this meaning, in this setup. We want to enable the model to learn this itself. Okay? Now, little bit how we understood, because if you go back last week, I mean, I'm not going that far down, all our learning, I gave you an example of how does the baby learn, what the steps it takes, what the steps we do. So, now we're talking about English, we know that words have multiple meanings. So if you think about it, there are homonyms where a word has two different meanings, like bank. A lot of such examples exist, they're called homonyms. When there are two closely related meanings, they're called polysemy, just like magazine, in the sense that both are noun, but they have different connotations depending on the context. Now our goal here, not that we are doing it today, or the researchers were doing 10 years ago, is to see that can the model or LLM learn the same word or have the same word but with different vectors, or if you think about it in the terminology of the today, same token bank have two different embeddings depending on the context. That's what we are saying here. If the bank has two unrelated meanings, then in the LLM's meaning space that we introduced earlier, there cannot be one embedding representing the token bank, because it has two meanings. So we want somehow the model to figure out that the bank has two unrelated meanings. So depending on the context, it can possibly have more than one or maybe two embeddings, which means different vectors, different probabilities, different setup, right? That's what we are trying to see. How would a model do? How would a model do, in this case, the best way to represent the embeddings for a given token? Okay? This was a paper. Normally, when I teach the other courses, I always tell, especially the graduate students who are about to go for research or something, you need to find 5, 6, maybe 8 papers that are fundamental in your area, right? And then make sure that you understand. In the case of large language model, this is what we do. How many of you are here who are doing the financial management or something like that? The MBAs? Come on, no one? I need to ask every single one of you what you're doing here. Okay, the reason I was asking is that anyone here has heard the Black-Scholes formula? Yes, no, maybe? Alright, fine. Ignore that. Let's stand with the generative AI. Now, this was a paper published, majority of the Google's researchers, but there were a couple of University of Toronto people as well. The paper was called Attention is All You Need. If you want to do something about the large language models or transformer architecture, make sure that you read it. It's about 40 pages, I think, roughly. Pretty dense paper, but then easy to implement or easy to confirm that this works. So basically, what this did is it defined two things. It defined attention and it created an architecture called transformer, which is a specific kind of network architecture. Now keep in mind, what I said last week, when you are designing an intelligent system or AI system, you're figuring out weights and biases, and you're figuring out what kind of structure your network will look like. Earlier today, I gave you some examples of how researchers figure out that for simple functions, what kind of architecture is needed, not by designing it by hand, but figuring out how the model kind of structure itself. But still, they did that two hidden layers, one with 5 neurons, one with 3 neurons. They started with some lot of experimentation, which is what usually happens in the research. And then they came up with this architecture called transformer, which is the same as feed-forward network. Now, feed-forward network, we saw this in the sense that when you have multiple layers and each layer is sending or feeding its output to the next layer as input based on attention. So 2 things that we are going to focus for the next maybe 30-40 minutes about: attention and transformer. Not going into too much mathematics, not going into too much implementation detail. I left the slides here. I'm going to skip them because if somebody has an interest, you can go over them, understand them, but let's try to get the intuition. Okay? So let me give a very high level block diagram, if you may call it. Basically, if you think about it, I introduced the deep neural network having the layers. Now, this is a block. So literally what is going on is that we haven't yet defined attention. So I'll come back and then explain to you intuitively what's going on inside there. But if you think about it, there's a block called transformer. That block of the implementation inside is doing something called attention. Attention. And then what the attention is doing, and these transformer blocks are stacked over each other. So there are 2 transformer blocks here, which means that there are 2 inputs and 2 outputs. Can someone tell me, based on your understanding of what we have been talking about for last hour or so, and what I mentioned about the transformer and attention, what exactly is going on here? There's plenty of information on the slide itself to give you an idea. Tell me what exactly is going on here. Okay, don't go in those many words, in the sense, just tell me like what exactly is based on this slide. Yeah, you may be right, but how did you get to that point? What makes you say so?
Analyzing the words by the various features like about the verb or nouns, and then it is connecting it to the sentences accordingly.
Right. So what is going on is that iteratively it is trying to give context to the words. So the initial sentence input was John wants his bank to cash the, say something else. The first transformer discovers that wants is a verb. Can it be something else? Yeah, wants is a noun also. Right? Your wants. What do you want? Your wants. Similarly, the cash is a noun also. So at the first iteration, this transformer is discovering that wants is actually used as verb here. Cash is also used as verb. Then the next transformer discovers that his is referring to John. Bank is a financial institution, not the river bank. Cash is a verb. So what is going on here? At each level, the transformer is discovering more and more about the tokens, the context of their token. Because the want could be different, the cash could be different, the bank could be different, his could be referring to whoever. This is what the transformers do. And how do they do it? They focus on attention. So let me ask you 2 questions here. Do you appreciate the fact that this is needed? Yes? Because English is not context free. It is context dependent or context aware language. So a good or an efficient or effective language model does require the knowledge of the context to appropriately decide which is the next common word to be used. You all agree with that? Right? So, the issue was that, and this was again about 10 years ago, the researchers all over the place, Google was obviously at the front of it, were trying to determine what architecture, what concept would let models figure out the context of every word to correctly determine how to form the next word. So, what they came up with a concept of attention. So really what is going on here, it says the transformer is the architecture, the two-step process to update the hidden state of each of the word, which is really the context. In the first step, it's called attention step, each word looks around and try to figure out its own context. So which word around a word has greater impact on its own meaning. So if you think about what I'm saying here, the bank trying to figure out is cash. So a cash gives a context to this bank that is not related to river. His, John, wants bank to do something to cash. That means it's a verb, not that it's a noun. So the whole idea was that every word, if it looks around itself, which is how you discover, right, whether it's an adjective or a verb or a noun, because you're looking at the sentence. Transformer is doing exactly the same thing. It has two phases. So first phase is attention phase, which is really every word is looking around and trying to find out what is the relevant context, and they share information with each other. Is that point clear? I'm going to ask this question, that how will they share information with each other? Obviously, if you are the humanities or the management background, you may not know it, but the science guys should really be able to figure out is that how do you share information with each other. Anyway, and then the second step is called feed-forward step. All the neural networks are feed-forward network. I just mentioned a couple of minutes ago that the output of one layer becomes the input to the next layer. That's what is feed-forward step. So each word looks around, tries to find what its context is, and share that information with each other. That's where they can figure out which is the best output. And then they move on it to the next step, which then repeat the same attention step and then continues to feed it to the next layer. So usually you will find that transformer is an architecture which is doing an attention step, a feed forward step. By stacking a couple of these transformer one over the other, what was discovered that this kind of attention, this kind of context can be discovered by having a few transformer layers. So if you look at one of the modern large language model, you will see that there are up to 15, 20 different transformer layers introduced in there. So not only you have input layer, output layer, you have hidden layers, now you have transformer layers as well. What they're doing is that they're trying to construct context for each word. Make sense? So intuitively, that's what is going on. So we started with single neuron, hidden layer, softmax, then in between now we are introducing the transformer layers. And I'm saying that they are stacked because there are more than a few transformers that are discovering this. So our network is now looking like this. You have input, you have stacked transformer blocks which are trying to discover the meaning around each sentence, and then trying to come up with a much better understanding of what a network, what a sentence looks like, right? Now we can go and we will go a little bit into each of these things, because at the end of the day they are all neural networks, deep neural networks. There are layers, there are neurons, there are weights, there are biases, nothing else. There are mathematical probability functions as well. Not go into too much math, but this is what we're going to do next. All right, so something is missing from here, but that's fine. Let's move on. So it's just a quick recap. Static embeddings, which we saw earlier, example of only two things, single alphabet and a combination of two, which are static embedding. Nothing is changing. They are static, the probabilities are known, and then you figure out what exactly. The problem is such is that you take another example, it. How does it know what is it referring to? Is it referring to chicken? Is it referring to road? You know it, the road doesn't get tired, it's only the chicken who can get tired, so it must be referring to chicken, but a model doesn't know it. How would the computer know it? Right? That's what is basically the context is about to do. If you have static embedding, there is no way you can figure out what is it referring to, because you know it, that's why it's referring to. Okay, all right, so let's continue to build with this intuition here. Meaning of a word can be different. It says should be different, but think of it this way, can be different in different contexts. I mean, really speaking, the should is fine, because if it is not different, they're not different contexts, they're same context then. The contextual embedding is that, and I mentioned this already earlier, that if you have a different meaning in some context, the word will have a different vector or a different embedding. Right? How do you compute these embedding? That's what is called attention. Okay? Let's look at the example of an attention. And again, I have separated out the intuition from the mathematics. So let's see if everybody gets the attention part intuitively. So what's going on? We have multiple layers, right? At this layer, it comes across the chicken, the road, and then it says it. At the next layer, what it is trying to do is that it can only refer to either road or a chicken. It can also refer to the in some cases. So what is going on is that the attention phase is limiting the scope of what it should be considering. We haven't gone that far when you see that the tired is referring to it, and then from its basic understanding says the tired is never associated with road in my previous learning, so the tired must be associated with chicken, which means that it must be referring to the chicken. That's what is happening in each stage. So what the attention is doing, attention is saying that, and if you go by two other slides earlier, each word is looking around and seeing that which one of these words around me have a higher impact on me. How? Based on the prior learning. Okay? If you had two vectors and try to find the impact of the component of each of those vectors, how would you do that? Dot product, right? If you create a dot product of two vectors, you find the resultant vector. Really speaking, if you think intuitively at a very simpler level, what we are doing, we said each of these tokens are also vectors. That's what the embeddings are, sequence of numbers. When you multiply each of these things to the other ones, if the embeddings were discovered correctly, that's how it's calculating. So if you think about it, each vector in a way is a matrix. It's calculating dot product. So by simply creating dot product of a word with every other word surrounding it, the model discovers, based on the prior learning, which one of these words have higher weightage. Once you do it in multiple layers, the expectation is that it will figure out the context correctly, and it does. So the dot product, what it does is that if you're multiplying two vectors of the same dimensions, the wherever there is a higher value, it will basically get enhanced. The lower values will get further lower. That's what the dot product does. The resultant vector will have that kind of behavior, right? All right, make sense? So what is happening here is this. It takes the surrounding tokens at the previous layer, will do the dot product, and then basically creates a weighted sum of vectors, and then they become input into the next layer. By iterating this process a few times, what was observed that the network or the model is finding out the context almost correctly every time. Right? Basic simple math. Do you get it intuitively as to what is going on there? Yeah? So I'm going to bring in the first mathematical slide, but it's exactly same thing what I said. I'll be happy to go to and fro to explain what was going on here. So x1, x2, xi are the token embedding. Each x represents a word. The word is represented by a set of numbers that we have talked about. What we are trying to do is a weighted sum of every single of these vectors weighted by their similarity to xi. So let's say we are trying to find out the attention of xi. Which one of these are going to have more impact on it? You calculate a score by doing a dot product of xi with every xj. Let it go through the softmax because you want probabilities that which one of these have higher probabilities of impact or attention on xi. You get up with a number, and then basically higher the number, higher the probability of the context that it might have. So same thing that I talked about earlier, represented mathematically here. Does it make sense? So if we started with here, this one, now it looks like this. So you say that xi, we are trying to find out it. What does it refer to? Then you basically go and then calculate the xi's vector multiplied with every other vector. Now the assumption is that that vector, which is the embedding, which is the weightages find in some higher dimensional space, will have values which when multiply would say it could either refer to road or to chicken. And in the next stage it will say tired. Tired is most likely going to go with chicken, not with road, so it is going to be associated with the chicken. So this one is represented here mathematically. Make sense? Okay. So how is it done? Little bit more before we make a stop in about 9 minutes. So the way it's going on, and again a very high level idea. So xi, x4, instead of using them directly, they are being represented in 3 different matrices. Query is the element being compared. Key is every preceding input that is being compared, and the value is the output that is coming in. So if you think about it, xi is a key, x1 to x7 is the query, and then the value is coming is the output, which in the next one will become input. So 3 things that we are computing: query, key, and value. Query is the current element being compared. Key is everything prior to that. Value is the output. The value in this phase will become a key in the next phase, and the query word will keep moving one word, one token at a time. Make sense? If any of you want to implement the attention paper, what you would end up doing is writing some matrix calculations using these matrices: query, key, and value. And in every iteration, the value from the prior iteration will become key in the next iteration, and the query will move one token at a time. Sorry? Any questions? Yeah.
How does the model generate new tokens while a model has attention on previous layers key queries and key values? Then
Okay.
how
So let me stop you right there and see if you can rephrase it. Model is not generating any token. Tokens are all coming as part of input. What the model in this phase is doing is that finding out which token has higher impact on the other tokens. So if you want to rephrase your question, then it's not generating any new token.
Model takes tokens from previous layers.
No. So the layers are all same. So tokens are all same. What is going on is that it's looking at each of these tokens one at a time and then trying to calculate which preceding token had higher impact on the current token. So in this example, this is query, xi is query, everything here is key. The output becomes value, the value of this layer becomes key to the next layer. So what is your question now? No. So the mod. Oh, okay. Hold on. Are you saying the new token means the next token here?
Model takes tokens from previous layers.
Yes.
How does it generate new tokens?
No. Okay. So there are two separate things that you're talking about, if I understand correctly. So in the generative AI, we are always saying that it's always generating the new token, right? Now, what I am saying today, to generate this new token, it has to know which token has a higher impact on this new token. This process is simply discovering which one of the prior tokens have a higher impact on whatever is the next previous token to the next. Before generating, it is trying to figure this out. Does that make it clear? Okay. So let's say this one more time. Anybody else actually has a question or thing? I'm just going to go one more time to explain the entire process, but is there any other question? Okay. Yeah.
Weighted sum we are taking of the query with the keys.
Yes.
So at each layer, after going to each layer, we will have the value of that alpha.
Mm-hmm.
So that alpha will be for the entire layer or for each combination of query and key.
Each combination of query and key, exactly. Actually, each combination, each query. So what your goal is, so let me just combine the two things, and that's where the confusion was, right? See, the goal of the entire LLM is to predict the next token based on what it has seen so far, right? So the end goal is this, to predict the next token. But how do you predict the next token? By looking at this, because this is not context free, right? So if it has a token called it, now the model needs to figure out first, what does it refer to, right? In this example, was it referring to road or chicken? To do that, even before you can predict the next token, you need to apply this transformer logic. And that's where I'm explaining, without even going to how the next one will come, what is it referring to? So this layer, and the next one is determining that the it is referring to chicken, not to the road. Is that clear? Right? And your point was that the weighted sum is being calculated for every one of these tokens. It didn't matter for cross, the, because, but it mattered for it, because it was not clear that whether it is referring to this noun or the other noun. Make sense? No? Okay.
So actually my question is, for entire layer, we are taking this weighted sum of alphas, or we are computing alphas for each query and key combination and then finding out which makes more sense?
For each key query combination. Right? And then figuring out, see, here's the thing. For this one, it makes no difference because this is unambiguous. This is unambiguous. This is unambiguous. This process makes sense only when you come across this. You're computing it for everything, but it makes meaningful for this only. So we are computing for everything, but it's only meaningful in this case.
So the meaningful combination only will go to the next layer.
Everything will go to the next layer. Everything will go to the next layer. But what will happen is that you will see that in each subsequent stage, this will be a higher value, everything will start going down. So it will emerge as that this one is the one which requires more attention. Does that make sense? Okay. So then what is going on is that we have query, key, and value, and then in a way, this is what is going on. The word like it, so it will have an attention head. So what will happen is that each layer will have attention head, which means that many times this process is repeating and it's figuring out that what exactly is it doing. One of the attention head will end up matching pronoun with noun, which is the example we saw just now. Other one might be doing the resolving the meaning of homonyms like bank, which is the example I'm not showing here, but I said that once it figures out that it can only belong to either road or chicken, then it will figure out that tired. The tired has to be associated with either road or chicken, and then it will determine that a road cannot be tired, it must be chicken that's tired. So these are all attention heads, or the pieces of the information that it is trying to figure out that which of the meaning of a word is relevant in the current context. Another attention head might be trying to link two word phrases, like Joe and Biden are representing one single concept, Joe Biden. So there might be a lot of different attention heads which might be required for one single sentence, right? Okay, we take one more slide and then we'll stop. Generally speaking, GPT-3, and this is old, a few months old, not GPT-3o, had 96 layers which were doing the transformer, 96 attention heads each. So really speaking, every time it was predicting a new word, there were 9,200 odd attention operations being carried out. So it's a whole lot of calculation before it predicts one single word here. 96 heads, 96 layers in 96 transformer layers basically that it's doing. Yeah. Okay, so it could be both, because if you think about it, in the unsupervised learning model, every input is learning as well as generation. So it doesn't matter whether this sentence was fed to it to begin with or it generated all of it until this point. This was an example to show that how does it determine what does it belong to. So the basic functioning of transformer layer is independent of where the sentence came from. However, when you are doing the multiplication, those multiplications are happening based on the probability that is already learned, right? So it doesn't matter whether this was generated or this was given as an input. Okay, the attention head is basically, so in this case, in this example, it's trying to determine the pronoun and trying to figure out which noun it is referring to. There are different type of attention heads, because this is again something that we know our language, the peculiarities of our language. So one is this one, which was matching pronouns with nouns. The second bullet point says that trying to resolving the meaning of homonyms, whether the bank is a financial institution or bank is the side of a river or a water body. So one attention head is simply trying to do that. The other one is trying to figure out that if there are two words which are added together, right? Like Joe Biden. So it's telling the model, saying that don't think Joe is separate and Biden is separate. They're together, a single semantic unit. Any other question? Sorry? Oh, self-attention is basically the same thing that we are trying to say here. Every word, when it becomes a query, it is trying to find the attention on itself. That's what we are saying is that the self-attention layer. Every word at one point or the other will calculate a self-attention in the sense that what is the impact of the words surrounding it on itself. Okay? Now, one thing which, this is a very simplistic model that I have shown here, right? So the thing that I have not mentioned here in this example, this is only showing the words or tokens that is seen so far. In one version, it might be looking at the words on the other side also. In some cases, it may not be in the every pass, but in some layers, it's looking at both sides. Okay? All right. Yeah, I think we should stop at this point and then we come back and continue a little bit more on attention and transformer. We'll skip the math portion. I'll leave it for if some of you have interest in them, then you can continue on those. Okay? All right, let's break a little bit. And I promise it'll go much more more softer concepts rather than the hard math going forward. Yeah, should stop a little bit. So when do we meet here? 15 minutes. 15 minutes? Okay. Okay, shall we start? You guys ready? Getting very low voices. All right, let's just start here. We lost another 10 minutes here today. Okay, so just a sense of how many different neurons we're talking here. This is an example from GPT-3. Input vector has 12,288 values. The output vector has the same size. One hidden layer which has almost 50,000 neurons. Just these three layers, if you get together, all of them, if you get the numbers calculated here, so 49 going into 228, 1228 going to another 1228, that becomes actually 1.2 billion weight parameters. And then there are 96 feed forward layers, so total 116 billion parameters. That's the number to be calculated for figuring out one word. For every word, it's calculating 116 billion numbers. So at some point of time, and this is something we'll start talking from tomorrow onwards, that is it really economically feasible? What is the value being added to do that much calculation? On the other hand, maybe our mind is doing the same amount of calculation, hundreds of billions of calculation every time I speak a word. It's probably happening back here, right? So either that or our designs are all really very bad. They are very inefficient because we're doing billions of calculations, right? Okay, this is just a quick recap. The next few slides, a quick recap of what we already did. This time it's just showing into a vector representation. So W is a matrix at one for each, one for query, one for key, and one for value, which is an output, and then Xi is the query word that we are using for every single iteration, right? Very simplistic view. The actual attention head is somewhat more complicated. I have a few slides, probably about 10 slides out there going there, which I don't intend to cover. I already mentioned, I haven't left it there because there's a lot more involved, a lot more mathematics, right? We talked about this when we stopped. Query represents the current context or the focus of the model, whatever the word we are looking at. Key represents the elements or feature of the input data. Majority of the time, the words that we have already seen, but in some implementations on both sides, looking at the words that we have seen, plus the words which are coming in as well. And value is the value associated with the elements or features, which is really the dot product of the query and the key that we get together. What the attention mechanism is doing, it's calculating the weight, measuring the similarity between the query and the keys. How do we do that similarity? It's the dot product or cosine product, if somebody remembers the vector arithmetic. So we're doing the cosine product here, or dot product. These words determine the level of importance of each element. Higher the weightage, higher the number, lower the importance, lower the number that will come out. The values are weighed by attention weights and then produce the final output, which goes back to the input as the next layer. Similarity that you're doing, you're using the dot products between query and the key. Summing up, we are multiplying by the weights that we were doing earlier also. So this is really what is going on. You calculate a score, you send it to a softmax, and you get the output, which is really a collection of probabilities. So doesn't matter what calculation we are doing. The beauty of this entire design is that whether every action is exactly same for a neuron or from a neuron perspective. Whether you're looking at the attention, whether you are looking at finding out the probability of the next word, it's exactly the same calculations going over and over again. Now, we have not introduced or not talked about it, we'll talk about it in the coming few days. That's where the GPUs come in the picture. Because really speaking, if you think about it, what is going on here is that lot of large numbers being calculated, multiplied, or manipulated, which is what the GPUs are very good for. So the companies which are producing the GPUs, or one company that was actually producing the GPUs, makes the most money out of this new development here. Sorry? NVIDIA. Yes, NVIDIA was the company which was producing the GPUs. GPUs were earlier used in the computers to do the graphical calculation, or if you were in the gaming, or if you were generating a lot of big images, then you were actually producing those or using those. This diagram is roughly what I had captured. Self-attention, somebody asked, but this is exactly the same process that I talked about. You generate the key, query, and value vectors, which is really nothing based on each word, what is prior to it, and what's the output going to be. You compare the keys, you divide the score because in the calculation, and then combine it using softmax, and then add it all together, and you get the output, and then determine which word is affecting or impacting the current query more than the other one. All right, let's just move on here. Self-attention, somebody asked. Exact same thing. If you just look around, I mean, I'm just repeating it here, but that's exactly what is going on. Is it conceptually clear now? And what the goals of the attention mechanism is? I gave 3 examples basically, right? And there are multiple of those. GPT-3 had 96 different type of attention heads that they are looking for. Some of them are proprietary or like secret that they are using, so they don't even tell you what exactly is going on there. But basically, the self-attention mechanism or the attention mechanism is looking at the context of each word and then try to figure out is which word is impacting more than the other. The second example, as I mentioned, was that for if you think about, it's trying to find out where a word may have more than one meaning, trying to figure out which meaning is more meaningful in a way. And then in the third example I gave was that when you have 2 words together, they are supposed to be treated as a common, like Joe and Biden are treated together. All right. Now, based on what you have seen so far, what are the advantages? What are the benefits you think are there? What are the advantages, if any? If we are spending so much money in calculation, there's got to be some advantages, right? So let's look at some advantages. One clear advantage is parallelization. Okay, earlier neural network, which obviously we didn't spend too much time on, whether recurrent neural network or LSTM networks, they were all sequential in nature. You couldn't parallelize them. So there was a limitation of how fast, how much they can produce. So the transformer model lets you run a lot of computation in parallel. Scalability. These models can actually produce or handle large data sets, produce a lot of different inputs, and then basically once you can do that, you can deal with larger data sets, you can produce the larger output or have even larger context windows. The larger context window is the third point here, is a long range dependency. Depending on how big is your context window, you can go back 5 words, 5 sentences, sorry, 5 paragraphs. I think it is. No, it is not. Okay, now it does. Yeah. All right, thank you. Sorry, guys. So depending on what the context window is, that you have a long range dependency. If you have a larger context window, it can go back to not just 5 words, 5 sentences, maybe 5 paragraphs. So depending on how large your context dependency, all of this is coming because of transformers. And then obviously there's flexibility, because once you can figure out the attention head mechanism, attentions, and try to basically compare Joe's and Joe's, Bill and Bill, if you're referring to 2 different bills, which one is referred by which word, obviously it makes your model much more powerful. Now, there are variants of these transformers. Now, some of you may have heard of these. I'm just going to give you a very brief introduction of these things. Now, because we are not going into the details of these things, I thought I'll just introduce, so I just added a few more slides, actually very early this morning. GPT, which is probably the most commonly known, you guys have known this or you know it in the sense that that's an autoregressive model, generates text one word at a time, can perform few short learning tasks or even one short learning tasks very well. BERT is the Google's model, which is based on the transformer. It's bidirectional, which means it can look in both directions. As I mentioned earlier, I didn't give the example. The examples were all from GPT, but the Google basically include that its transformer can look on both sides. It uses a masked language modeling rather than predicting the next word. It basically tries to predict the missing word. And because it's trying to predict the missing word, it can look on both sides also. There are benefits, there are advantages, there are drawbacks also. T5 is a specialized transformer which is good for text-to-text translation. What it does is that it basically tries to build the longer contexts in the sense that where words are not translated from one language to the other language just as a word, but as a longer phrases. So it's a specialized transformer which does the text-to-text translations. Comparatively, if you think about it, they all have their different ways of looking at it. The GPT is unidirectional, which is very clearly understood. BERT is bidirectional. T5, because it uses the encoder-decoder mechanism, is bidirectional in encoder, unidirectional in decoder. The decoder is where it's translating from one to the another language. The next row explains you encoder, decoder, encoder, decoder only. The pre-training objective, majority of our examples in this last 5 days came from GPT, which is autoregressive language modeling. BERT, I mentioned, is the masked language modeling. What it does is that it hides one word, tries to predict it. Once it matches with the hidden word, it knows that it has learned that and it moves on. That's the pre-training objective. Denoising for T5, which is really doing the translation, is similar to BERT's because the encoder phase of the T5 is exactly same as the BERT learning. The longer spans of text, because it's not trying to translate word by word, it's translating sentence by sentence or even larger, the concept by concept. That's what it is doing. Task approach is, again, it all depends on what the goals were. The size is another important factor of comparing the two. BERT, I mean, again, this is an old one. Gemini has improved the BERT big time, but the BERT had 340 million parameter. GPT was way ahead. This slide is pretty old, actually. T5, because it's only limited itself to the translation, it can handle up to 11 billion parameters. A lot of Indian languages are also now part of T5. So you can take a Spanish text and convert it into Telugu, for example. How well it will do, I'm not sure. I know Spanish a little bit, Telugu none whatsoever. So I'm just giving an example. So a lot of different variation on the transformer architecture. As it stands today, if you ask me, this is the most promising architecture that we have in the deep neural network. Will it remain the same a year from now, 3 years from now? I don't know. There might be other researches which have not yet been published. Actually, there are major players who started with the deep neural network, and then on the attention side and also on the transformer side are already being a little bit skeptical of having this as the future. So there is an understanding that something different, either both from architecture perspective or from the conceptual perspective, will have to come fairly soon. Okay? All right. So let's just very quickly summarize what we did in terms of the transformer. We learned or looked at attention as a concept. The whole idea of attention is enriching the representation of a token by looking at the contextual information. We saw the example of these. We also saw the example of different type of attention heads. I gave you 3 examples. One was the exactly looking at the incorporating contextual information. Second was that if the word has different meaning, trying to figure out which meaning is more meaningful here, or by combining the 2 words. GPT-3 has 96 different type of attention heads, which means there are 96 different type of information theoretically they are looking for. Not all of them have been published, some of them have been, some of them have not been. I gave you an example of just 3 at this point. The result would be that the embedding for each word will be different in different context. So something I had mentioned this earlier, bank has 2 meanings. So you would normally not expect that the bank in the GPT-3's meaning space will have only 1 embedding. It will have 2 embedding. It may have more embeddings as well. The contextual embedding is what is important, because just the embedding of bank is not relevant. Bank in the context of what you're looking at right now is what is important. Some of it has been studied, but the meaning space of the model has not yet been fully explored. I mean, researchers are still trying to figure out, trying to make sense of it, trying to find out where exactly the meaning is, or the latent space or capability that was not explicitly trained appears from. It is still an active research space. Any questions? Yes.
So nowadays computers are equipped with a special chip called NPU, Neural Processing Unit. So firstly, what is an NPU? And secondly, why only laptops have that and not dedicated desktop computers?
All right. Now this is one of the questions which I will say that I have no idea. Okay. This is not my area. I don't know actually. If you want something, let's take it offline. I will find out something and let you know. But I have not really seen too much detail on the NPUs, and I'm not even sure why the second part of your question, that it's on a laptop or not. My laptop is almost 8-9 years old. It definitely does not have an NPU, I can tell you that. So sorry, but if you want, we can talk about it separately. Anybody else? I mean, there's GPU. The Google has come up with its own called TPU, which is the Google's own response to challenging NVIDIA's kind of position or monopoly. Yes, but then it does it implements their own software as well. Any other question? Hopefully, which I know or have an answer for. Anyone else? How many of you have played Housey or Tambola or something like that? Housey. So normally they announce a prize saying that those who have not really filled any column yet, right? So I should ask that those who have not spoken or asked any questions. Let's have one of those ask a question here. Anyone having a question? Those who haven't yet spoken or said anything? No? Okay, all right. So this is the section which I do not intend to spend too much time on it. So I'm going to skip this out. Lot of conceptual, lot of mathematics. If you have an interest, as I skip out, you just let me know. We will spend time on it. But basically, it's more math and a little bit more complexity from 2 perspectives. One from math, one from actually not looking at one head, but multiple heads, and then trying to explain that. So this is exactly what it looks like. You saw this version before. There are stacks of transformers that are running in parallel. As the attention head moves, or as the query and key changes, you have the information moving in slightly sideways as well. So long and thanks for, so moves on, long and thanks for all. What you're looking at continues to shift. This is what needs to happen every time. These are the keys. These are also the input, the values, and this is an this is a transformer stack, and at each level, each transformer might be doing something different, right? So it's fairly complicated structure. The next few slides are trying to explain that. Feed-forward network, which is doing the ReLU also. So what it is saying is that some layers, not necessarily all having sigmoid or softmax, that becomes part of the architecture. Why one versus the other? Like someone asked me last week, that's all the research that they have seen that this function performs better or this combination of functions and layers and number of neurons perform better. That's what it is. If you look at all of these models, that's what the architecture is different. The basics are still remain the same. Layer norm, which was one thing that I did not spend time on earlier. It is only meaningful when you have stacked transformers from one layer to the other layer, and I am not necessarily going into the detail, but if you think about it, all they are doing is defining, if you see that mu and sigma are two moments of the probability distribution. First one, if you see, is like an average. First one is an average. The second one is standard deviation, right? So literally what's going on is that they are computing a layer norm, which is a variation of a z-score, which is something like a normal distribution, trying to find a single number that you can take from one layer to the other layer. Same calculation or same example, but showing exact calculation at a very high level that is going on at different time stamps or at a different time and different stacks. Again, I'm not planning to spend time on it. Basically, multiple blocks, it's repeating in each block. And this is the point I was trying to make earlier, and this is a very recent paper which they say that the attention head is shifting the focus from here to another parallel stream, which is what the same thing we saw earlier, that it was here and it was trying to find out where exactly it's getting attention from or which prior stream it's getting attention from. So literally what they showed is that you can view attention head as moving information from one token into the neighboring token or tokens. Excuse me. I'm going to skip the token embedding, positional embedding, because this is a little bit of a math I wanted to talk about, but we will skip it. Go over it. If you want to have a conversation, we can have the conversation in the next couple of days. But this is basically, if you think about these, about 10 slides or so, this becomes the final transformer model. They're talking about how exactly what we saw before we took the break, which is the one example of key value query pair gets transformed in two different ways. One, when you have a multiple stack of transformer, and then you have in parallel whatever the number of context window is. If it is 8K, there are 8K such stacks of transformer working together. So that's exactly what we are doing here, and we are getting a few examples here. All right, so basically, as I had said earlier, that I'm not going to spend time on it, I just walked over it. There are probably about 12 or maybe 14 slides that I skipped here. Intuitively, what they're doing, as I said, is stacks of transformer and in parallel. Thing that you need to learn about was the finding that was done a couple of years ago here. This one. Because what is going on is that you're shifting the attention when you're trying to find out is from one stream to the other stream, which is what is literally what was observed or what was intuitively figured out. So keep that in mind. That's what is happening in parallel when you look into it. Okay. There are a couple of other things that we have mentioned in passing. One referent here is unembedding layer. I'll just give you a little bit of an intuition before we actually go on to this page. When I said in the very early days, like second day or maybe third day, that learning is both weights and biases, but also the interconnection between the neuron. Then when we were learning either on fourth or fifth day was regularization, when we said that the intent is not to memorize, but to generalize. And one of the ways in generalization was regularization. Third thing, if someone remember, was dropout. And I said that the dropout is basically when you drop out the output of a neuron or ignore it. In the transformer architecture, what they have is an unembedding layer also, which basically does the same thing. Rather than dropping out output of a one single neuron, what it does is that it has an unembedding layer, which means in the meaning space that we talked about, it may take one entry and unembed it, which means saying forget it. So it can do that as well. That's also part of learning. Think of it this way, it discovers that, okay, whatever I had done up until so far for this particular token is all wrong. So it unembeds it. So that's also part of learning. Okay? All right. So, any questions? I'm at Q&A.
Sir, can you give us some idea about what is happening after the stack of transformation, like that language modeling?
Okay. All right. So I think both of you asked a very similar question. So see, there is nothing new that is happening here. So if you think about it, all the LLMs are doing is predicting the next word, right? When we started on the day one, our examples were so simple that it was easy to predict. And I said that, I mean, in a way, actually, that's what we're going to do this. So it's a good question. We are trying to recap what we learned, right? So what we said is that all these large language models are doing is predicting the next word. And then we said that there is no single word. So each of these words are probabilities. And then it will pick up the word based on the probabilities. Then we said that, you know what, if it always picks up the same answer, it is not necessarily the interesting thing, or it may not be the context that you have. So then we said that you have prompt engineering, which is basically letting the model to know what your intent is, or you want to modify its behavior. All good, right? Then we said that each of these words, up until today I was using the term word, or let's say token, is somehow represented into a space. That space is a very high dimensional space whereby these tokens by their proximity show their closeness to each other, right? Then we said that even though that's the case, and once we started making it bigger and bigger, we said that now there are these sentences where either you have a pronoun or you have a word whose meaning is not very obvious, because the language is such that they have multiple meanings. So within the same goal of predicting this word, now we have a larger problem to discover this. To solve this problem, we said that we use what's called transformer, which is based on the concept of attention. So whatever we talked about today was only trying to make this process more efficient. Eventually, this goal remains same. So what we saw that you had 96 layers of transformer stacked over each other, each of them doing maybe something different. One of them is trying to figure out what is the pronoun referring to. Other one could be that which of the context applies to the bank. Other one could be trying to get together, let's say, what's the bank you have? Punjab National Bank. So it might say that, you know what, Punjab and National and are not two separate tokens. You have to use them all together. So depends on what exactly you're doing. All of these are like sub goals. Your goal is still this, to predict the next word. That still remains. This is still solving the problem of understanding the context. Does that answer your question, or you want to modify it?
So that large language modeling head is doing essentially the same.
No, there's nothing called large language modeling head. Attention head.
Modeling head, that after the stack, in that flowchart, after the stack of transformers, we are
This one?
language modeling head.
Which one are you referring to?
Here,
This one, okay. All right, fine. Okay, so you're saying this word basically. Okay, yes. So in some way, shape or form, it is this part. The end of the result is still discovering this, right? The transformer is the one to understand this better. And for every word, that's where I mentioned in one of the earlier one is that to predict this word, there is 116 billion calculations being made, which is all happening here. So it's a lot of math going on there. Okay, all right. No, we got a little too further ahead of us. Any other question? This was a good question just for complete. Yeah.
As this math is totally new for me, sir, what we are getting in the key theory and value, as we had calculated dot product to calculate attention head. So what we are getting in query, value and key means we are getting numbers or words that we have to calculate the dot values.
Okay, so two separate things here. So first thing to understand that each of these tokens are represented by a vector. Those vectors are the numbers, right? That's what the position space is. So every token is represented by a number, right? And then what happens is that the learning tells that, and which is what the transformer is doing is, so the sky, the blue, for example, right? So we don't know how these numbers are getting calculated or assigned by the language model, but what was figured out is that the sky and blue, there will be some affinity. How do you figure out? You take this number, multiply the two vectors, sorry, and then take a dot product. What comes out here is some numbers which seems to be indicating the blue is related with sky. That's all it is. Now, this vector is randomly assigned numbers, not randomly, assigned numbers by the model itself. That's what is going on, right? Now, when you are looking at this word, each word by its turn becomes a key. Whatever preceding it, becomes a query. What is preceding it is a key, and then you update the values based on the dot product, and then it becomes input to the next layer, the next layer, the next layer, right? These embeddings, these vectors could also be changing. As a matter of fact, as I said, that there's an unembedding layer where some of these things could be dropped also. I mentioned here that just one vector, the blue may have multiple vector embeddings in the space, like bank is. The blue may also be, because if you think about it, blue is just not the color. If somebody is sad, that feeling is also described as blue, right? If somebody has got, somebody's got hurt, right, or beaten blue, like heavily beaten, that is also the blue is used. So blue in itself may have multiple embeddings possible in the space because it's a different use case, right? Okay, any other question? Okay, feel free to think about it or just ask. So let's see. We're going to be kind of concluding the generative AI portion, and then we go on to the use cases and the other socioeconomic kind of repercussions. So let's see the recap here. When we started, there's a traditional machine learning and there's a generative AI, right? So let's try to compare them into 5 different ways. The primary task of traditional machine learning generally was classification and regression. All kinds of models exist there, right? A lot of techniques out there. Some of them are kind of straddling between data science and machine learning because they are all together overlapping with each other. Generative AI primarily is generating some new content, audio, video, text, whatever the case may be. While doing that, and we saw the example, it can also be doing like summarization or sentiment analysis, because they can all be expressed as the same problem as generative AI. Traditional machine learning definitely needed the label data, because first it is to be trained or told, whether it's classification, regression, or any other kind of a problem, it required label data, and which is where actually the drawback was, because trying to get the label data was a problem. Though companies got creative, I gave you the example, CAPTCHAs are all the label data sets. Every time you were tagging your friend, your family member in an image, you were providing them label data, right? Generative AI models can work with unlabeled data. As a matter of fact, you would see that pre-training is all with unlabeled data. So that's a huge advantage. The output, traditional machine learning model is doing classification or a prediction. Just like as I said that you can create a regression model of GDP growth. If you got the model right, you may be able to predict what's the GDP growth is going to be next year. This can be expanded to anything. People have built model where they have said that, let's say you are maintaining a huge data center. So there are models that are going to predict that which CPU is going to fail, which hard disk is going to fail, etc., etc. All kinds of models can be built. Generative AI is usually creating new data or synthetic data, right? Model complexity. Traditional machine learning, it varies, but generally they are simpler compared to the generative AI. There are usually more complex models in generative AI. Interpretability, in the sense that if the model is giving me a result, can I go back and figure out why it gave me this result? In traditional machine learning, it generally is easier. You can go back and figure out why the model is saying what it is saying. Not so easy with generative AI because we do not know a lot about how the neural networks are working. Though people are learning. I mean, the researchers are going after, that's how we know how the semantic space is, how the word space is, that's how we know how attention is working. That's how we've seen the examples of that it not only has the tokens that we understand as word, but also has some tokens which we don't know why it's creating them as a token. So there are a lot of things which are not known, a lot of things that we are trying to figure out and learn as we go along. Okay, let's continue to look at a few more dimensions of this. Generative models are generally more creative. Traditional machine learning was not doing anything creative. Generative AI is writing, or at least attempting to write haiku poems. Not great, not like Shakespeare or not like Kalidas, but they are doing something. People have used the GPTs to write stories. Stories are not really very good, but we are there somewhere. But at least what they are doing very well now is that they have learned the style of, let's say, Shakespeare. So if you provide what researchers are doing right now, your own story, and say, can you rewrite it as if it's written by Shakespeare? It has learned to do that fairly well because it has figured out the style of one author. If you give it a story, then it will convert it into the author. So it can change a few things. Unsupervised learning, all right, one bad label there. I'll fix it later. Generative model can learn without labeled data, which is really the most important part that we are dealing with it. Dimensionality. Now, I have mentioned this earlier also. In typical machine learning, the focus was always on reducing the dimensionality. We were always trying to reduce the dimensions of data in which we are dealing because that's what the mathematical modeling makes it easier. You know that if you're trying to do regression analysis, the focus is that can we get a linear regression function or quadratic function or polynomial. You don't want, so you're trying to reduce the number of data sets. You start your data analysis with 50 different columns of data. You're trying to avoid where, okay, this one is not necessarily, it is very sparse. We don't have data available, not use it. Then you try to find out that, okay, this is same as this column. So let's not, so always trying to reduce the dimensionality. Generative models can work in high dimensional space, no problem. They create their own higher dimensional space. So that's really always a problem. Always the benefit of the generative AI model. Evaluation, the quality, that's very subjective right now. There are no analytical, formal, mathematical way of comparing one model versus the other. So a lot of open research areas that we are currently working on. Okay, before we move on to the applications of generative AI, which is literally the last topic for today, trying to get into what can you do with it. We just summarize a little bit. I just spent like, I think 2 slides or 3 comparing the traditional machine learning with the generative AI. Any questions? I did not use the term expert systems and things like that, but if you think about it, they were all supervised learning model, like an expert codify their knowledge and then you somehow represent it and then you also then use it to display or come up with a result. So, any questions so far? Yeah.
Just an observation that, you mentioned about evaluation, very subjective, like how to find out how was the output of that whole thing. Like only humans can understand or?
Okay, so two things there. First of all, when I say evaluation on this slide, that's not what I meant. The evaluation here was that the comparing two models and the quality of two models, not the absolute quality of one model. But inbuilt comparison there or evaluation there is your answer as well. So if you think about it, from that perspective, the reinforcement learning is one way of evaluating the quality because that's what is going on. Because in reinforcement learning, you're telling the model, did you do well? Did you do good? Did you not do good? You're penalized. You're getting 60 out of 100 or 50 out of whatever the scale is there. So from that perspective, for one model, because you're providing it feedback, you're basically trying to improve the quality. That's always there. Similarly, something that we talked about earlier is the GIAN models, which are that there's a generator model and there's a discriminator not model. There's generator module and a discriminator module, and they're always telling the discriminator is always trying to finding fault with what the generator module has produced. So internally, these models are getting evaluated and improved on. This specific bullet point was if you have two, there is no formal way right now to say that this model is better than this model. You may have trained model A, somebody else may have trained model B. Now, I as an independent observer, I have no way of saying which model is better. We haven't yet discovered or learned that. I mean, yes and no both, because at the end of the day, if you think about it, whatever we are doing, these are all human decisions, right? It's just that we're trying to figure out
What is the better quality output?
that definition is on us to define, yeah. But and that's one of the reasons, because we are not able to define, we are not able to even implement it. It's the same thing, right? It's a very interesting question because in the next few days, that is what we're going to talk about. So I'm going to take an example. We're going to go into the applications of generative AI, then we will take the examples which are out there, and we will look at from ethics perspective, from the risks perspective, from biases perspective. So in a way, if you think about it, we will be evaluating these models, but all those cases will be evaluation of these models in a specific use case. And even there, we are not sure. So where the current research is to identifying where there are moral problems, ethical problems, biases issues, risks, other societal risks, the issues related, the assigning of responsibility, all of these kind of situations. I mean, there are the assignment of responsibilities even today. If you think about our legal system, when something untoward happens, the laws determine the responsibility of who is responsible for this behavior or who should be punished. So same kind of issues will come in when we let the models take action on behalf of us. That who's responsible? Is model responsible? Is the model developer responsible? Is the programmer responsible? Who's responsible if the mistake is being made, right? So these are the issues we're going to talk about in the next few days. But good question. Anybody else having a question here before we go on to the applications? Okay, if you don't ask a question, let me ask a question. What applications do you have in mind for generative AI? I know one of you were doing the edge detection, right? Or something similar to that, right? What about others? What kind of applications do you think if you had access to, let's say, the best model available today, what applications would you be using it for? Come on. Virtual? Sorry, virtual what? What is it?
Virtual friend, sir.
Virtual friend.
Yep.
Oh, virtual friend. Okay. All right.
High scope in solar industry, I guess, or like PV installation, solar installation.
Uh-huh.
Basically, it is installed on rooftop.
Uh-huh.
So, like it should be aligned with the direction of sun.
Yes.
So, in there, we can use it to get it aligned.
Okay.
Also, it requires like a regular cleaning, and it is very not much feasible to go like on the rooftop, go on that top.
So here's a question. I mean, that's a good example, but let me ask this question here, right? A couple of years ago, I actually taught a course on blockchains, basically cryptocurrency and blockchain. There were a lot of examples in various places, a lot of them from India, where people said that, oh yeah, they're building an HR system using blockchains. I had to really ask that, but why? I mean, I gave an example of Occam's razor, right? I don't know if any of you looked into it. If there are multiple solutions available, pick up the easiest one. So the problem that you are pointing out are genuine problems, right? But I'm going to say that those problems have already been solved without using the generative AI, for example. One of my job before coming to the academia was at Bank of America. Bank of America constructed a building 10 years ago, which already had the window shades, which were automatically tilting depending on the temperature and weather outside, whether to let the sun rays in or keep them out. Because if the goal is to heat up the building, it was letting the sun rays come in. If the goal was to keep it cool, it was blocking the sun rays out. And that was being done without generative AI. Now, theoretically, you can say there was intelligence built in. Yes, because there were sensors inside, there were goals, whether you want to raise the temperature or lower the temperature. And then there was the mechanical motors, which were actually controlling the angle of the shades. All of that was done. And it goes back to the question, what is intelligence? 10 years ago, even in America, that was great. Now, it was great for two distinct reasons. One, it was first of its kind. Two, even though it's known, not every building is doing it, because this was a new building, they were able to do it. Older buildings are not equipped to do that. So it's not happening. First time when it happens, it looks like this is magic. Once people figure out how was it done, then it's just a matter of every building getting renovated, and every building then calculates, okay, what's the cost, what's the benefit? Will I recover the cost in 10 years, or it will take me 50 years to recover? If it takes 50 years to recover, the people who are living in that building says that we're not going to be here for 50 years, we're not going to pay for it. So it doesn't work. So, I mean, my example, what I'm saying is that it all depends on it. But think of an application that you cannot do today with the today's technology, and that you can use to do with the generative AI.
So we can use Gen AI in education for education purposes.
Yes.
And for like we can bring back historical figures to life, and so that the students can understand that better. And we can also use it for hearing and impaired patients. We can give instructions to them at offices or their official systems are there. So they don't have to feel left out, or they have to ask someone. They can go somewhere where it is installed, and they can talk through it.
Okay, so you mentioned three things. So I definitely agree with you that education area is one, but let's just go into more detail to see what all possibilities exist. Now, bringing back historical figures. Okay, if you take the historical out for now, right? Narendra Modi created the hologram images in 2014 itself, right? So technology exists. You could create Einstein also, in hologram today. So that one I would say that is independent of generative AI. Even in 2014, it was possible to create a holographic image of anyone, right? So yes, it's an example, but it doesn't require generative AI per se. Your third example was about the people with limited natural abilities, right? That's what you were saying. So that's definitely one where we could say that rather than building the chatbots for people with natural abilities, let's build the chatbot or something like chatbot with the people with limited abilities. So that's definitely one area that I can imagine that we'll do. That's good example, but let's try to think things which are possible now, which were not possible without the generative AI. Yeah. Oh, you mean to say that can it be used in legal system? Yes. So that's another example.
Because there are, talking about Allahabad,
Yeah.
not this is currently anyone part of the
Yeah.
but there are a lot of advocates, so it can replace in future.
Okay. So let me give you two examples, and I have to bring in the topic again, but this is all good. Let me give you two examples of generative AI being used today. In US, it's used for helping in sentencing. I mentioned this earlier as well. Now, helping in sentencing means what? A typical legal case has 2 or 3 different phases. A charge sheet is filed, which means whoever is prosecuting, whether it's an individual or a state, is filing a charge sheet means against XYZ that you committed these crimes. Then comes the defense stage where the person who's being charge sheeted is allowed to give their side of the story, which is a defense saying that I didn't do it, we didn't do it, or whatever the case may be. Then it goes to the determination of the fault. Now, depending on the kind of system, it could be a judge finding fault, or in US, it's jury that finds a fault. Once the fault is determined, then comes the phase called sentencing, which means that it's already established that the person is at fault. Now, how much should he or she be punished? That's called sentencing. So, the AI has been used for helping in sentencing. Now, why that? Because the laws are never, the sentencing laws are never definitive. So, even if anybody who's familiar with law, or if you're doing in research, there will be that if you are found guilty, you may be punished up to 5,000 rupees of jurmana and 6 months of rigorous imprisonment. Now, judge has a leeway, whether he gives you 5,000 or 500, 6 months or one. Lot of time you may have heard of it that you are, the person is found guilty and was taken in judicial custody till the court rises, which means that the judge may be giving that judgment at 3:45, the court rises at 4 o'clock, so this person's punishment is over in 15 minutes. So even if the law allows up to 6 months of prison, judge might give it only for 1 day, right? So the AI is used in helping the sentencing. So that's one area. There are issues with that. We're going to talk about that in the next couple of days. It's also being used to actually create a case note, like either from the defense side or from the charge sheet side. The examples there were that it just made up everything. It made up the laws, it made up the cases, it made up the names, and it was a totally bad document generated. So theoretically, yes, it can be used. Is it there yet? No. I mean, there are published papers which actually are saying that the ChatGPT was used and has produced a very bad output. I'll see if I can get some examples for you, but yes, legal cases, yes. Has it been used successfully? Yes, in one case that I'm aware of. No, in one case where it's not been used. Even where it's been used successfully, we're going to examine it from the perspective of bias and the ethical and morality of the situations. All right, one more example before I go to my slides.
Sir,
Yeah.
Used to generate meta world where there can be bots like you and me having their own intelligence, and a person from real world can enter in this simulation with his own intelligence and can live the moment.
Okay, so you bring in a lot of different things. So metaverse is a separate technology. Yeah, metaverse, yeah. And it exists without generative AI as well.
The use of intelligence and bringing a real human into that picture.
Okay, who is a real human? Sorry? No, I mean, these are all very deeper questions actually, right? Who is a real human? Am I a real, sorry?
We all are in a matrix.
No, that's not what I'm saying. So you don't make it more complicated, because what you said can be broken down in 5 different ways or 5 different things, each of which are, in my mind, are undefined. So if you take just one simple example of who is real human, am I the real human? Are you the real human? Is the person who is driving a car outside a driver real human, or a person who is cannot see is a real human? It's very difficult to define who is a real human.
It's like the world of robots, and we are the outsiders.
Okay, now we're going into all make-believe world. So
Is it classified as species, like there's species like it works on issue, and there's species which works on like
even then the world is very complex. So in one of my hats that I wear nowadays, right, I work with the people who are intellectually or developmentally disabled. Yeah.
so you mean God is a human, real human, and we all are the gods in this
I'm not even going there. We're not even talking about that. So if you think about it, yeah, it's okay. Are you being discouraged to ask the question? No, it's fine. All I'm saying is that when you are trying to establish a problem, see if you can define the problem itself. What I'm trying to point you out is that in your setting up of the problem, there are a lot of undefined sections of that problem. It's very difficult for me to tell you who the human is. Who are we trying to model as human? Right? Is a 6-month-old baby human or not? A 6-month-old baby's world is very different from your world than my world. So who are we calling human? Right? It's a very open question. So, and it's a both philosophical question, ethical question, moral questions, all kinds of questions rolled into one. So we're not even going there. So if you think about it, Google had discovered this entire thing. The Google researched everything. They never actually brought it to the people until ChatGPT came on board, right? Why? Because they were trying to deal with all these problems of not giving the right answer, people thinking that whatever they see coming out of the model saying as absolute truth. It's not. We don't even know. See, these are the questions we're going to talk about in the next 3 days. Where is the problem? Or is there a problem? But there is other part of the question in the sense that the generative AI, because it's generating, can be used to create virtual worlds. Yes. So if you are a gamer, how many of you play games on computers, right? So generative AI can be used to create more realistic worlds, more futuristic worlds, because that's all the generative AI does, because it creates. If you're creating the world today, a game designer actually visualize the world. You can use generative AI to do that. Rather than you creating it, you specify, you describe. Let generative AI create the pictures. Generative AI can also be used to create worlds on the fly, which means you playing the same game as against someone else playing the game, they may see totally different worlds with the basic functionality. So a lot of things that you said are possible, should be done, or is being done today, but some of them are not yet well-defined problems. Okay, all right, so let's just take a few examples. Some of it are based on the case studies that I had pointed out earlier. Arts and design, that's one area generative AI is being used. Visual arts, music and audio generation. Many of you have seen probably, some of you mentioned that you have used these kind of examples. AI generated art, graphic design, AI composer, sound design. I'm not going to spend too much time on it unless there's a question, just ask the question. I have some slides where I basically talk about it. AI generated arts, generally using GANs, because what's going on is that generator generates based on the input and the discriminator basically evaluates how well it is, and it keeps on going automate, keeps on going, criticizing till it gets an optimized output, right? The process of creating AI generated art, if you think about it, I have this slide in some cases, not all cases. The basic flow is same. You train, you first collect the data, supervised or unsupervised, you train, you generate the new one. Human curation, that's what we were talking earlier. Will the human be responsible? Someone is going to tell us that, is it a good, is it not good? This is called the reinforcement learning human factor, or RLHF, reinforcement learning by human. I'm not sure what the F stands for. Let's say human factor, RLHF. Okay, so AI generated art. Let's look at a few other examples. Music and audio generation. It's happening quite a lot. Environmental sound, the ambient noise is being generated. Character voices, the game NPCs, what their voices could be, they were already being generated using electronically. You can make them even more authenticated, natural, innovative, whatever you want to call it. Futuristic or imaginary sound, that's what I meant by it. So you can have the you can have a character built how a Martian would sound like, and let the game character has that kind of sound, right? Another example I had it is generative AI in healthcare and biology. Lot of different areas. Drug discovery is something that is very actively being researched for from all different areas. I may have another slide on this at some point of time, but in general, understand this in the sense, trying to find the drug candidates, trying to find the interaction of the molecules, trying to find the feasibility of a specific module. Medical imaging, a lot of it is happening both in the stage where you're trying to detect is not the right word, interpret an image, but even before actually generating the synthetic images. Clearly none of you are doing medical, but are you familiar with any of your friends who is in medical world, being doctor or anything? How do they do their experiments? What do their labs look like? So there are two kinds of labs, right? In some cases they use cadavers, right? Because they have to experiment on people before they can operate on a live body. Then there are radiologists, or the people who are working with images. They need images to experiment or learn, right? Lot of ethical questions come in. Can they use yours and mine's images and x-rays in the lab? Yes or no? I mean, yes they can, but unless I give the permission, they can't. So nowadays the generative AI is used for synthetic data generation, for doing the experiments, to be used in learning, to be used in examinations and things like that. Personalized medicine is another big area where pharmaceutical companies are thinking of generating designer drugs. So they could build a drug for you specifically. Right now, if you think about it, each drug has the problems or side effects. So if you take 3 medicines which were not specifically done for you, you may end up having side effects. So one of the area where pharmaceutical companies are working on, can they produce the personalized medicine specifically for you? That's another area where they're using. I have a more detailed example of the drug discovery. Again, you're reducing the trial and error by lot of information that is done in real life, by letting it be done by the language, by the model itself. So it helps reduce some trial and error. It actually speeds up. It actually reduces the cost. Has it been used effectively, successfully? Still a questionable thing. They're doing it. Whether we don't know in the long term, this will be something that would show up as a very effective use case or not. I talked about medical imaging. Well, I think I kind of covered all of them. Personalized medicine, also I think I covered this. Now, personalized medicine is basically using your individual data, electronic health record. So anytime, every time, if you think about it, India is not there yet, even US is not there yet fully, not in a unified way. But imagine if there was a database that has every single time you fell ill, every single of your test that was ever done, every single medicine that you ever took, then in a way the model can build you virtually, not a friend one of you are looking for, but virtual you, and eventually can say that if you have this problem, this is the best medicine for you, because it has all the history of all the tests ever done for you, every time you fell ill and every medicine that you have taken. So eventually it can generate a medicine for you, right? So that's possible. There is a related science that's going on here, which is really, there is a group of people in US, multi-billionaires basically, who are working on anti-aging medicines. Basically, they're trying to see, can they remain youthful for whatever time they want to be. All of this requires you as an individual, your entire history, your entire genome sequence, and then a lot is going on, right? So that's one way on the personalized medicine. Even if it is not your individualized medicine, there could be treatment optimization if the model knows your history. So actually I will say that more than virtual friend, probably this is more likely that we have a virtual you being created. Mentioned about the genomic analysis, predictive modeling is again very experimental, but it's being mentioned about it. All right, let's move on. Education, some of you mentioned, that's a very, very positive or actively researched area that's being worked on. Two ways to look at it. Language learning, that's an easy one, in the sense that because natural language processing is one of the reasons why the generative AI came into being. So conversational agents, a lot of this is being done. One other thing, if you think about it, at least in US, even here it's possibly can be done. India also has a 3-language policy. US has 2-language policy. So other than English, you are expected to learn one more language while you are in high school. So one other thing that they do is it called embedded learning, which is really not the embeddings we had seen, but embedded learning was that spend a week or 10 days in the country whose language you're learning. So if you're learning French, you either go France or you go to local France. I don't know how many of you know or not, the Canada basically has a French Canada and an English Canada. So you go to Canada, which is a French area or French state, and then you learn French there. If you're learning Spanish, you go to one of the Spanish-speaking countries, etc., etc. Language learning is something that can be done by creating an embedded space where you're interacting only with characters who are speaking, let's say, Spanish, if you're learning Spanish or Telugu or Malayalam or whatever the case may be. Personalized learning content. How many of you are familiar with Khan Academy? Right? Khan Academy is experimenting with personalized learning content. They have a system or a model called Khanmigo, where they're saying that we are building a friend or amigo or someone who can help you based on what you are learning and what you are trying to do, creating the personalized learning content. To some extent, which is more related, is adaptive learning path. That's Khan Academy was already doing, in the sense that you give an introductory test and it figures out a path for you or individualized path for you. That's another possibility in the education area. I think I talked about language learning. Yeah, it can give pronunciation feedback. It can help you build vocabulary. It can correct the grammar. It can provide cultural context if you are making a statement or a sentence. All of it is possible today or is actively being worked on, and is one of the few positive applications that the generative AI can produce. Think of it. An hour ago I said that how much calculation that is going on, right? For each predicting a new word, we are doing hundreds of billions of calculation. We have to find out some use cases whereby it is all meaningful. Otherwise, right now it's just cost. Several $100 billion, close to $1 trillion have been spent by companies to do this. I'm not sure how many of you are keeping track of it or not. How many of you are familiar with nuclear energy? What is nuclear energy? A power plant, a nuclear power plant. How many of you have seen a nuclear power plant from distance only? Has any of you seen?
Most of us have seen that web series
Okay. Aye. Where I am from in UP actually, so we had a nuclear power plant very close to us, so every time I pass by it, you can see it. There's one in Aurora, near Bulandshahr, right? There's a nuclear power plant there. US had stopped making new power plant. Even India is not making a new nuclear power plant. Aurora was probably the last one. There are a few in South India as well. Partly because of the risk, like Chernobyl, that's what US did. You know who is buying the nuclear power plants? Microsoft did. Google's doing it because their power needs are so much that they can't find from any other source. So Microsoft has recently bought a power plant which is in US about 150 miles from my home. It was closed, it was not being used. Microsoft has bought it. Why? Because the needs of electricity is so much to run these language model that they're seeing in few years future down the line, there's no power available. So there has to be some effective use cases to justify a nuclear power plant to generate or predict the next word. Right? There has to be some good use cases. Okay, all right, so language learning. Let's move on to the next area. Business and finance. Again, business and finance is one area where any new technology gets sold first, and it gets sold for all wrong reasons. So it is what it is. Marketing and advertising, I mean, a lot of it is happening. Will it replace the creativity? Probably not. I mean, being creative is very, very useful. I can give a lot of examples where the creativity beats any technology. But on the other hand, the technology can make creative campaigns even more creative. That's always possible. So one of the way the marketing and advertising is happening is the personalized campaign, dynamic content creation, because if they know who you are, they can feed you the content that is specific to you, your taste, and things like that. Right? Now, just to give an example here, not necessarily the generative AI, but where the technology combines with creativity works. So, how many of you, I mean, I think you're all familiar with McDonald's, right? They're all here, and the Burger King also. Those are the two big chains basically that there are smaller ones as well, but in the burger space or the fast food space. So what the Burger King did, and without using generative AI, I'm just giving you an example of combining technology and creativity. When the mobile apps were out there, so you could find location, right? So if you have a location and if you have the intent, which is very important in converting someone from marketing to someone to actually having actual transaction being happening. So Burger King carried out a campaign a couple of years ago where they said that if you are within 50 meters of McDonald's and place an order with Burger King, then you're going to get a very special deal. So think what they were doing, because they can locate you where you are. They were able to find someone who has a high intent. Are there any marketing students here? Okay. So you know that if you can figure out a customer with high intent, that's like a gold mine, because then you have only one step, which is the conversion of that intent into a transaction. So what they did is that they said that if I can locate, or if we can locate people who are within 50 meters of McDonald's, which means they are about to make a purchase at McDonald's, send them a message saying that you order it right now and you're going to just get like it for 10 cents or 1/10 of the price or whatever the case may be. And that was a very successful campaign. There were people walking into McDonald's but placing an order for Burger King and then walking out. So I'm saying that there may not be a direct example of generative AI, but you can use it to combine the technology with creativity and come up with it. All right, so outside the marketing, then financial forecasting. That's something very actively a lot of companies are using the generative AIs for. I mentioned it earlier, the 10Ks and 10Qs, which is really the publicly listed companies need to file their statements every quarter and every year. Those are used for learning about the company, figuring out all kinds of information that's possible, predicting their growth as an individual company, as a market segment, as an entire market, generating those reports based on the data. That's another possibility, but then it doesn't necessarily require generative AI, but you can always do that. AI chatbots are very common. Many companies have started doing or utilizing them. Can someone tell me, we talked about it earlier, what is an AI chatbot versus another or a regular chatbot? A typical chatbot, chatbots have been there for 10 years, are following some kind of script or a decision tree. You'll ask a question and then take a path and all the way down here, right? Whereas the AI chatbots are based on generative AI. Given certain basic parameters, they should be able to converse and be able to deal with any situation, right? So that's the AI chatbots are doing. Here's a case study. I'm not going into the detail. This is a Walmart's AI-driven marketing. There are some examples. We'll keep coming back to it, but dynamic content creation, that's happening a lot. A/B testing, that's what you can do. You can generate multiple of the same thing, like multiple offers being sent to different target customers, and then figure out which one is working better, which one's not. Contextual relevance, I gave you an example about the user location and the intent as displayed by, because you're walking into a McDonald's, you're probably intending to buy a burger, so give you an offer right then and there and place the order. Emotional targeting happens all the time. Generative AI can only make it more relevant. Financial forecasting, AI chatbot, we talked about it. Some new areas. Virtual and augmented reality, we talked about it, virtual worlds, right? Basically for gaming, can give you more adaptive content, more realistic content, more engaging content. It's possible, right? Climate and environmental modeling. This is something which no one mentioned yet, but that's one area where the generative AI potentially can be used, because one of the limitations we have today about climate and environmental modeling is the amount of data that we can process. Now, we're building this massive hardware, massive structure. Hopefully, we can look into climate patterns. The fact that these patterns are not understandable today because of the limitation of our closed form models. When I say closed form models, means we are using equations that we understand, that we can use. We have always been studying the climate and environmental environment based on the concept of reducing the dimensionality, because if we are calculating by hand or by computer using the known mathematical equations, we are always trying to reduce the dimensionality. The large language model, as we saw, are very good in working with numbers in higher dimensions. Our examples so far were the numbers were representing the words. These numbers theoretically can represent anything. So if you think about it, if you generalize it, we have now models or systems that can work with numbers in a very high dimension. So there's a possibility that we learn about climate and environment in a lot better way. Robotics and automation, no one mentioned this yet, but there are generative designs that can happen. Robots can be trained to work on generative AI models. That means that, scary part also, that they are not anymore taught one task. If you think about it, robots are not new. The robots have been there for 50 years almost, right? In US consumer market, I don't know here, do you have the robo cleaners or anything like that in the Indian market? Not yet. So there's a company called Roomba, 10 years ago, that came in, which built the robots. So there's a cleaner that is a robot. Basically, it goes and cleans the stuff, whether it's your house, whether it's your pool. So a lot of these cleaners are out there. There are robots out there which will mow your grass. So you leave it out, it will mow your grass. So the difference in the generative AI is that all these robots were taught one task. General Motors have been using robots to do tightening the bolt. So there's a robot, its only job is that every time a new part comes, it picks up a bolt, it tightens it up, moves on. So now you can potentially build The robots which can do more things rather than just being trained on one task. So there are things which one of the project that I do to one of my classes to predict the use of AI in hospitality industry. Not sure if I saw it here or not. Robots are replacing in US the human waiters actually. So you place the order, a robot brings your whatever you order to your table. Robots are replacing if you go in a hotel and you ask for, let's say you forgot your toothbrush. So the toothbrush is delivered to your room by a robot. But all these robots are like one task or limited task robots. There's no generative AI capability. All that they know or all they have been programmed with. I ask for a brush, somebody on somewhere says that, okay, go to room number 301, deliver whatever that is. So robots only knows that how to get to 301, which includes actually using an elevator also. So it comes there and then you get, in a way, a notification that the robot's out there. You open the door, you pick it up, it goes back to its station. So one type of training that can replace with generative AI with new types of training. Dynamic word generation, we talked about it, adaptive environment, procedural content generation, actively being worked on. Manufacturing, I think I mentioned this to some extent. Not my area, so I can't talk much about manufacturing, but if anybody here is in production management or operations management, you should probably be knowing a lot more about it. This is probably something that I can't talk too much about. I have no idea. All right. Something that will take us to what we are going to do in the next couple of days is this part. There are a lot of challenges. Bias and fairness, I have mentioned it multiple times, not defined it. We're going to define it. We're going to see what the challenges are. Privacy and data security, huge problems. We touched upon it a little bit in terms of the corrupting the prompt, corrupting the model. There are a lot of things that have happened. We have seen the issues with data security. The large language models have known to unknowingly share secret data or the secure data or the private data. There are intellectual property and attribution issues. That are they stealing intellectual property? Are they copying work that they shouldn't be copying? So a lot of these are unknown areas. So we have to think about those as well. And those are some of the areas we will talk about in the next few days. Okay, any questions? We spent like last 20 minutes in talking in terms of a lot of potential areas. I also mentioned that there has to be some good areas to work to justify a lot of money. Hundreds of billions of dollars that have already gone in and will probably continue to go into this area. Are we ready to use it? I mean, right now, many of these companies are all basically losing money. Every time they predict a word for you, it's probably costing them a few rupees in Indian currency, literally. So if they're giving you for free, they're just trying to get you used to it. Eventually, they'll all cost money. Or we have to find use cases which justify this kind of Okay, any questions in terms of we summarize what we AI and we look at the applications and we look at the problems or issues that might be there. There are no regulations. you have seen that okay. I mean, sometimes you went to a place, let's say, I'm not sure your specific use case where someone from good intention said, okay, I'm take away the bad part of your X-ray and only show you the good part. I don't know how much value is there. So I'm not sure if I follow your question.
Important on AI. Like, I don't remember the exact name, but something has been ongoing discussion in the US Congress, which was headed by Sam Altman, and it was unilaterally supported by both the left and the right. The idea was to regulate AI. However, its slightly sinister interpretation was the big players like Google, Microsoft, etc. want to regulate AI so that small open source tools cannot grow and compete with them.
Okay. So there are a lot of things that you said, again, depending on the specificity. US Congress, Sam Altman cannot do anything. I mean, that's an individual, basically. He doesn't have a role in the government. But yes, there are a lot of stuff is going on. Some of it is good, some of it is not so good, some of it is. And think of it, when an individual or when a private agency is doing something, it's not totally altruistic, right? Or when the charity happens, there is some motive behind it. Some altruistic, some may not be that altruistic. So my point is not that there is no regulation. My point is that the regulation is missing. And no one knows what the right regulation is. And there's always, and this is not unusual, whenever there is a new technology, nobody can predict it and have the rules and laws in advance. We don't know that, right? Now, there's always a public policy question. Should you encourage innovation and then regulate it, or should you regulate it from day one and stifle the innovation? So that debate has always been there, and in every field it's been there. Any other question?
How an message of AI is correlated with water crisis?
So how is what? I missed the first.
One word generation
Yeah.
is correlated with water crisis.
I don't know how it's correlated, but if you think about it, like, I mean, if we are using a lot of energy, somehow it's using the water also. And water is used even today, actually. Even if you leave the generative AI out, all of these companies have massive data centers. Google has a lot of data centers, right? And they are using water to cool the heat. They generate the heat, a huge amount of heat. I mean, their data centers is huge, huge data centers, like millions of computers in one location, and it generates heat. And they use a lot of water, which gets evaporated once you circulate it. So yes, it's a problem, and unknown problem. That's why they are trying to generate the nuclear power to save some of it. Yeah.
Sir, I have a general query.
Yeah.
Like we talk about the advantages and applications of Gen AI.
Mm-hmm.
Surely it is going to be very helpful in future aspect. But as we know that India is a country with a large number of unskilled workers, and surely it is going to be for those who are skilled. They are only going to use that Gen AI and all. And with the growing rate of population, like the numbers are, India is the most populated. So like it is going to increase unemployment.
Okay, so see, this is also an age-old question, right? I mean, I agree with many of your part of your statement, which are factual. India has growing population, true. India has unskilled labor, true. So there's no argument with that. But when you project it from there, that will it be that the two parts that I specifically want to say that we don't know for sure. A, you said that only skilled people will be using it. We don't know that. That's number one. It all depends on how you or the people like you who are going to be either using it, building solutions out of it, or creating use cases, who do they create use cases for? Do you make it easier for someone who's skilled, or do you use it to create solution for those who are not yet skilled? Right? That's one thing. Second thing, it's always been an issue in terms of whenever a new technology is introduced. Now, many of you are very young. When the computers being introduced in the bank, and I'm talking late 1980s and 90s, they were opposed by like tooth and nail, that everybody will lose the job, things like that. Every time a technology comes, and I can go back in the history. Now, obviously, I have not seen that, but I've studied that. When the cars were introduced, and I'm talking about 1920 in US, before cars, there were all the buggy-walas everywhere, right? These buggy-walas were used. The thing was that, what will happen to those guys? But then, again, what happens is that the nature of the jobs move. Yes, it might require skills, but that is a problem. But to say that we do not want to develop is not necessarily the answer, right? That's what I would say. If you think about it, and I have seen that world here, prior to 1970, India has only 2 car companies, Ambassador, Hindustan Motors, and a Fiat, Paul Automobiles, right? There were only 2 types of cars. There was nothing else there. People can't even buy the car because these companies couldn't even manufacture the car. And they wouldn't manufacture the car because they said, oh yeah, nobody's going to buy the car. This country has seen the days when the scooters, to buy a scooter, and I'm talking about 1960s, 1970s, you have to get in a line and you say, I want to buy a scooter, they'll say you'll get it in 3 years. Right? So, I mean, it's the same thing, because you look at the priority, you say that, would it be used by the skilled person, unskilled person? There's no right or wrong answer. You need to find the right answer, right? Okay, one last question if anyone has before we stop. Yes, no, maybe? Okay, great. Thank you. So when we meet tomorrow, we'll start going in some of these things, the risks, the costs, the benefit to the society, regulations, and whatnot. All of the interesting topics. Okay, great guys. Thank you. If anyone, thank you. If anyone is following the Google Classrooms, I actually uploaded some more documents. Yes, my intent is, and again we'll see, because I have prepared for it to convert this material into some kind of book, so I have uploaded some very early drafts of the chapters, so you can have a look at those as well if you want. Sorry? No. I don't think I've uploaded any third person's paper. You couldn't download? Okay, that I don't know. I don't know, some permissions, yeah. Okay. Yeah, you can check it later on. All right, guys, great. Thank you. See you tomorrow.